yeah.
Yes, people know. Karen, are you okay to stand here? Or
I will stand here.
we can give you
Okay.
the lapel mic if you want to move around.
Well, I decided to stay here because I have the money. Then I can just run away, and then it's yeah. The
can get
people
going whenever you
who
want.
are joining the seminar, the workshop online, and you go out of it.
Okay. Are we live? Yeah. Cool. Right, hi everybody. Welcome to day 2 of our workshop. I think we're a bit behind time already, so let me just pass straight over to Karen, who's going to talk to us today about this key topic of the workshop: interaction between PMP and maths education.
Thank you, Matthew, and also thank you to Yassin for organizing this. I have to stand right here.
No.
If you don't hear me and I move away or I'm running out, just give me a sign that I don't hear me. But it's also hello to the people online. So nice to be here, and thank you for inviting me for this talk. Actually, Yassin sent me an article, a draft article on the interplay of philosophy of mathematical practices and mathematics education, asking, Karen, can you have a look at it? And I was reading the paper, a very nice paper, and I hope you will publish it soon. I was missing some aspects, and I say also to Yassin, well, I'm missing some perspectives from mathematics education. And I thought, well, maybe this is an entrance to give a talk on the interplay of philosophy of mathematical practices and math education, or philosophy of math education. So I'm at the Center for Logic and Philosophy of Science. That's a place that also Yassin was joining for a couple of years, and also Fenner. Fenner left us for Loughborough, but actually for a tenure in Berlin. So, main role at the Center of Logic and Philosophy of Science is actually to support young researchers. We are a center of about 20-25 young researchers. Most of them are postdocs. We are 4 professors at the center. So what we have to do is just to support the young researchers. And actually the research I'm doing is during stolen hours, because I'm partly on the Department of Philosophy. I'm a hybrid. I'm also at the central level of university as the director of the doctoral training. And doctoral training at VUB University is organized not on topics. It's different from, for example, in France, where you have les écoles doctorales, and this is organized around a topic like mathematics or sociology or whatever. Now, in Brussels, it's organized over all faculties. So I'm dealing with, for human sciences, because humanities is part of it, with organizing the training for doctoral candidates. We don't call them students, and we don't call it education, but we call it training. So I'm a bit in between, and also my experience is that by the end of your career, you are involved in all kinds of commissions. So just keep in mind, young researchers or young tenure tracks or young professors, that by the end of your career, you have really to look for stolen hours to do some research. So I'm happy to be here. I was looking at my abstract, and I was reading again, because Yassin asked, Karen, can you send the abstract? So I thought, okay, take 5 minutes and think what you want to say about during the workshop. And I thought, well, I will clarify the concept of math education. What is it all about? It's like a container concept. So if we want to influence, and if we want to have a kind of interaction with this field, what kind of field are we thinking about? And I was also thinking to say something about domains that are included, because I'm also working on statistics and civic statistics. Are we also talking about data, big data? But my colleagues in medical science, they are very, very, very puzzled by small data. So it's all about data. I have to say that the Department of Mathematics at Brussels University is a very small department, very few students that go for mathematics. So they opened up the topic and they say, well, it's on mathematics and data science. And actually, the project that Fenner was working on at the VB was a project that we are running now on data science and the mathematical part in data analysis. Now, Dennis Sarikaya is working on this project, but actually he left also for a couple of months to Denmark. So it's a quite dynamic research group. I will make the difference with the philosophy of mathematical education. I did some work on that many years ago. And then in a second move, I will introduce some forerunners on math education who are focusing on the social and the cultural aspect. Be it Ubi D'Ambrosio, Ellen Bishop, Paul Ernest, Renuka Vital, and Ole Skofsmose, and Ruben Hirsch. And finally, and this is research I am doing with Joachim Franz, and actually I have to apologize to Joachim Franz, who's a postdoc at our center. He was doing his PhD research on explanatory proofs in mathematics, and then he did some postdoctoral research on that, and we came up with the idea to look at the field of mathematics education to see what mathematical or explanatory proofs can mean in math education. So this is the final part, where it is a research design. So I will present the research design, asking for some input if you can have nice comments on that. But this was too much. So I skipped a couple of things. I will not explain what philosophy of mathematical practices is, because most of you actually were from the real beginning part of the research community. I will not talk about statistics education, although I think it's quite interesting to make the comparison with math education. But I will concentrate this on the concept of mathematics education, then on the philosophy of math education, which is different, then the forerunners, and finally I will give some examples of explanatory proofs, although yesterday we had some examples, so I can go quickly through that, and focusing at the end on the research design or the research that we are planning to do together with Joachim Franz. Joachim is online, but as I understood, he can only react in a written way, but we can see by the time of the discussion. About the philosophy of mathematical practices. Last summer, we had a summer school on philosophy of mathematical practices. It was organized in Düsseldorf by Denis Sarikaya, and there was a nice overview given by Benedict Leuve. So if you would like to have a very nice and historically story of the foundation of philosophy of mathematical practices, you can ask Benedict Leuve to give his presentation at one of your workshops that you will organize soon. I was talking about statistics, and actually the article, which was, I did an article on that, on civic statistics. It was a book that was edited by Jim Ridgway, and so I will not talk about this, but what I want to say about it is that I think statistics is different from mathematics. We had a lot of discussions on that during conferences on statistics education. But in Flanders, for example, I'm from the Dutch-speaking part of Belgium. In Flanders, for example, and I was investigating the curriculum, statistics is part of mathematics. And some statisticians say, well, it's impossible that the mathematician is giving statistics and so on. So it's quite a different group. And I think it was the historian Morris who said that, well, the difference between mathematics and statistics is that mathematics has to do with certainty, while statistics is dealing with uncertainty. So let's move to the goal of math education. And I'm referring to the talk that Keith Weber was giving yesterday, and he referred to Brunner with the quote that, well, the goal of mathematics education is that we want students to acting like mathematicians. And this is a quote from 60, and I will give in a couple of minutes, I give an overview how the research field of math education changed over time, and how psychology came in, and afterwards how first psychology and afterwards the social aspect. So if you look at the definition or the description that is used by the OECD when they are implementing the program of international student assessment, the PISA results, then we see that mathematical literacy is defined as the individual's capacity to identify and to understand the role that mathematics plays in the world, to make well-founded judgment, and to use and engage with mathematics in ways that meet the needs of that individual life as a constructive, a concerned, and a reflective citizen. So here you have the citizen. It's citizen-oriented, it's reflective-oriented, it's critical-oriented. It was the description that was used at International Comparative Research of PISA in 2003. And as you can see, from 2009, they added an important part, a more technical-oriented part, a part on the content of mathematics itself. So mathematical literacy is concerned with the ability of students to analyze, to reason, to communicate ideas effectively, as opposed to formulate, to solve, to interpret solutions to mathematical problems in a variety of situations. So here we have, again, they added, I think it's always a discussion, what do we have to add, what do we have to emphasize? So here again, we have this emphasis on the technical, on the mathematical part of the literacy that Brunner actually was talking about, that they added more levels on the literacy part. And I think it was last year that I gave a talk on the difference between statistical literacy and mathematical literacy in a workshop that Fenna was organizing. And I was going really over time, I remember, and I didn't look to the chat, but it was a COVID format, so apologize for that, Fenna. So interesting to see how similar the concept of mathematical literacy and statistical literacy is, and how we can use it also for big data literacy, and so on. So each field can learn from each other, but now we are here to see what the input or the interplay between philosophy of mathematical practices and math education can be. To give you an overview of the math education research field, I thought it's interesting to see what kind of big conferences are going on and when they were founded. And I start with the International Conference on Mathematics Education, which was founded in Lyon in 1969. ICME, as a short acronym. And then in 1976, we had the International Group of Psychology of Mathematics Education. Mostly it's referred to as PME, and it was founded in 76. I'm puzzled with the order of the numbers. During the third ICME conference. And the ICME conference is a 4-year circle. It's a huge conference. I think one of the conferences, like 20 years ago, I met Gila Hanna. I was attending the top study group on argumentation and proof. And it was in Copenhagen. It's a huge conference of about, I think, 3,000 people. And there are also nice expositions where you can see how you can visualize mathematical proof, not only as proof by looking, but also in kind of installations and all very nice things that you can do. So actually for the exposition itself, it's worth to attend these conferences to see how inventive mathematics teachers are. Then later on, we have the European version of the ICME, of the International Conference. This is the European Conference, the conference or the Congress of the European Society for Research in Mathematics Education, which was founded in 1998. And then finally, at 1998, actually, there is the foundation of the Mathematics and Society conferences. To give you an idea of the size, I never attended the PME, but I'm looking at Keith. Probably you are attending or you are applying. Ah, really? Okay. So I thought we are complementary because I'm attending the international, the European, and actually the paper with Joachim Franz on explanatory proof is sent to the conference, the European conference, the top study group of proof and argumentation. So if we look at the dates, we can already see kind of timeline, and we see that psychology was the first concern or the first perspective in 76, and that we have to wait for the social perspective until 89. So let me explain a bit. We did a nice paper. I did this paper with Jean-Paul van Bendehem and Kathleen Koessens. Kathleen Koessens is actually an artist, a musician, but also a philosopher. And she's now actually the director of the Conservatoire at Liège. Since she moved from Brussels, and she was actually doing a PhD with Jean-Paul van Bendehem at our research center. But then actually she moved again to the artistic part, and we did a couple of papers together with Jean-Paul on the comparison between philosophy of mathematical practices and artistic research. And I'm still involved in artistic research, and it's quite inspiring. So writing an article with Jean-Paul van Bendehem is always a pleasure. He came up with the idea to say, well, let's look at mirror neurons. So it's kind of invention in psychology of mind. But as Jean-Paul pointed, actually it's the social that can be found into the individual, because the mirror neurons actually need the other to do the work, to interpret the meaning, to interpret the behavior. Also in the paper, but it's a paper from more than 10 years ago, it's 2012, we also explained the different influences by Piaget and Vygotsky, why Piaget was so important in Western Europe. And I have also to say that at PME, at 1985, Alan Bishop was giving a presentation on the social aspect of mathematics education, saying that we have to look at 5 levels of the social, be it the cultural level, and this is related to the history of mathematical ideas and how mathematics is embedded in culture, and there we have the concept for the first time. We have the societal level. It's the institutions in society concerned with math education. It's like the Ministry of Mathematics Education, for example, or the commission that is organizing the curriculum, for example. Then we have the institutional level. We have the different school systems, and we have the curriculum. And we have the classroom level. This is, and I'm referring to the talk of Brandon yesterday that I could not attend, but every classroom is multicultural. So we have for the second time the notion of culture, be it now connected to multicultural. And then we have the individual level. It's the learner from the social perspective. So in the paper, we gave an overview and a kind of timeline. So actually before 75, there was no connection between the psychology and math education. It's actually from 75 that there is the attraction from the attraction of psychology in math education. And it was actually inspired by the work of Piaget, and who is focusing on the child, concerned development psychology. And look at the bottom where I refer to the work of Vygotsky. They are from the same age, they are from the same period that they did their work. But Vygotsky was working in a Russian area. He was studying Siberian school communities, and he was looking at the learning procedures that were used there. And he coined the concept of zone of proximal development. And this is a kind of entrance to a concept that later on will be used when we focus on the social aspect and the background. So I'm now saying the concept, the background of students. So Vygotsky is coining this concept of zone of proximal development, what means that you start with the zone of the learner, the comfort zone, the background, and that from there you can go further. And you have to go further. I will come back to it when I'm talking about critical math education as founded by Skofsmose. We have, in 1985, we have the Bishop's talk on the social with 5 levels. And at the same time, we had this interest in ethnomathematics. Ethnomathematics, I'm referring to an article of Ubi D'Ambrosio. Before, there was some work done by Asher and Asher, Maria and Robert Asher, a mathematician and anthropologist, who were studying local mathematical practices of they called it non-literate people, but then it was not woke. So they spoke about non-Western or local people or indigenous people and so on. So then later on, we have to wait until 1988 for the foundation of the Math Education Conference. I will give you an overview of the conferences and what kind of topics that you can apply for. So I will start with the general overview of the ICME, a bit elaborated, and then shortly I will mention what is going on in PME, in the European Conference, and at the Math Education and Society Conference. So next year, it's a 4-year circle. We have the conference in Sydney, and it's the first year that they started, and I will give you an overview, that they started its kind of categories of topics. Until the last conference, it was actually divided in top study groups going from 1 to 40, and every year there was added another top study group, and you could see at the numbering of the top study groups if it was a kind of a new topic or not, because they never reshuffled the order. So the first one of the first top study groups is like proven argumentation, for example, and then also divided in the different levels. So let's have a look at the different domains now. So they are numbered 1, 1, 1, 2, 1, 3, and so forth. I was looking what is actually the categorizing that is going on. So I thought the first one has to do with all different fields in mathematics. So it's algebra, it's measurement, it's computational thinking, it's geometry, algebra, and so on. But it's also on the learning of statistics, so it's included, although they have also a separated huge conference on statistics education, and it's also on the learning of probability. So the second categorizing of topics is like, it's the difference of students, and it has to do with the difference in competences of students. Like, for example, the giftedness of the special learning needs has to do with kind of competences of the students that are in the multicultural classroom, and it has also to do with the background of students. So you can see under resourced context or ethnomathematics, there is creativity, there is also culture, language, and ethnicity. Looking at the third category, we see that now it's related mainly to didactics and to the school level. So you can see, for example, math education at the early childhood, at at the primary, at the secondary, all kind of levels. And there is also the topic on the didactics. So what kind of language and communication do we have to use? The assessment and testing is a very important issue. And there is also the data science. And you can see the newcomers is like 3.17 and 3.18, which is on blended learning, blended teaching, blended learning. We all are familiar with now because of the pandemic, and the data science. If you look at the fourth category, it's like teacher-centered. Now we see that it's related to pre-service, in-service. It's the knowledge in and for teaching. And it's also related to the level, so the primary level, the secondary level. And also the knowledge in for teaching is also divided in the primary level and the secondary level. What happens at 4.7, 4.8? It's a newcomer. So now they also talk about effect, beliefs, and identity of mathematics teachers, which is interesting. The identity and maybe, the beliefs of the mathematics teacher and what the teacher is thinking about, for example, the ontological status of the body of mathematical knowledge or mathematical objects, if it is fallen from the sky or if it is based on a human practice. Ruben Hirsch is saying something on that. And then the newcomer is now knowledge and practice of mathematics teachers, educators. And you see the newcomers, they don't have a level in primary and secondary education. They just start and they try out. And then maybe within 4 years, they need to split up in primary, secondary, but also university level education. And finally, this is a kind of, I called it new topics, although it's not that new. For example, philosophy of mathematics is quite old in this area. But you can see if we look at the newest, if we look at 5.11 and 5.12, we see that it's international cooperation and it's popularization. Popularization, I'm not sure how to understand that, but maybe this comes close to the civic mathematics, but I'm not sure what the concept is meaning. I know what it means, what the meaning is for civic statistics, and in society there are a lot of experiments and a lot of projects that are going on with people, from the street to get some idea of data collection and statistical analysis of data. So popularization, maybe we have to apply for this top study group to see what is going on there. The philosophy of mathematics and mathematics education, I promised to say a little bit of that. So as you can see, Paul Ernest is the past leader. He's not longer involved in this top study group, although he's, I think he's still active, although it's, with the COVID, I don't remember. I didn't see him after COVID period. So, but he's still active in the editing and publishing his journal on math education, philosophy of math. And I think Yasin had an article or Dennis submitted an article on this. So the conference on psychology of mathematics education, I will be very short on that, is this summer. It's in July. And it's in Haifa. I think it will also be organized by Ido Gal, who is working also on statistical literacy. And I give you an idea of the topics very shortly that are central to the conference now. So they will talk about socio-ecological issues shaping the future of the mathematics curriculum. Is this something where we can join, or where we can add some expertise from the philosophy of mathematical practices? It's on innovative research approaches to mathematics teacher, noticing. So it's on problem solving with technology, it's central. The multiple perspectives on mathematical conjecturing, and it's on theory and practice of designing embodied learning for mathematics. And this is also quite new. I'm also interested in this embodied learning. I will come in a couple of slides, I will come to that. So, and I was also happy to see that one of the keynote speakers is Paolo Valero, who is in Stockholm University. She was undergraduate in Columbia. She did her PhD and is the intellectual daughter of Ole Skofsmose, and she's the supervisor of Alexander Pais. Now, I'm not sure if it is ringing a bell. I know it's ringing a bell for Brandon, but actually it's not really only the social and the cultural perspective, but also the political aspect that they are emphasizing. So I was happy, and you can see on the talk, mathematical subjectivation is that sentence or changes for a terrestrial life. It will be a talk that is focusing on the political choices that we make in the curriculum of mathematics. Then I come to the European conference that will happen also next in a couple of weeks. So I will attend the conference with a research paper that I will present at the end, or just give you an idea at the end of this talk now. It's normally at this conference is also working with topic working groups, and normally I am applying or sending a paper for the top study group 10, which is on diversity and mathematics education and the social, cultural, and political challenges. But since I was working with Joachim Franz on explanatory proof, we sent the paper to argumentation and proof. This is still actually the top study group that they took from the International Conference on Math Education, and it's organized by Andreas Muchos Rentos. Finally, we have the Mathematics Education and Society Conference also this summer, so it comes together. I will just join one conference, the European one. And the conference is, I will give you an idea of the topics that are discussed. This is a small conference. It's about 40 people. The European conference now, the registration it's a growing community. It's 900. Psychology, I have no idea, but I think it's a huge conference. And the International Conference International Conference on Math Education is about 3,000. So this is a small conference, and they focus on the topics of the politics of mathematics education, the cultural and social aspects of mathematics learning and teaching, the sociology of mathematics and mathematics education, and then alternative research methodologies in mathematics education. So I attended 3 of these conferences, and I was looking for myself what kind of proposals did I, what kind of presentations did I, and then I have to conclude for myself if I'm looking at the papers that I did together with Jean-Paul van Bendehem or with Carlos Montero, who is working on statistics, or a single author paper. It's mainly on statistics, statistical literacy. It's also the philosophy and the curriculum of mathematics. And it's also on ethnomathematics. Looking at the conferences I attended of the European conferences, the last one, which is accepted, is on explanatory proof. But as you can see, it's not really my habit. I'm coming from let's say, so the statistics was one part, but main focus is on ethnomathematics. I'm working with anthropologists like, for example, Rick Pinkston, and we coined the term multi-mathematicy to emphasize the pluralist view on different mathematical practices. This was the main idea. And we have also the work on local mathematical practices with Erik van den Driessen. Is from Paris University. He's an anthropologist, and he's a mathematician and working on string figure making. Looking at the conferences I attended on mathematics education and society, and most of them, but they are also, it's a 2-year circle instead of the international conference. It's a 4-year circle. So you can see that also I was investigating the curriculum of mathematics. I was investigating together with anthropologists in rural areas on the teaching of mathematics at rural schools. And I saw, is that ready?
You're still 15 minutes. There's a question.
Okay, then I have to rush. Okay, how to deal with this time constraint? I will give a short overview of the forerunners. So Uwe D'Ambrosio is actually coined the notion of ethnomathematics. He passed away 2021. And there is now, you can see his book on ethnomathematics, where he explained what the concept is meaning. There was a tribute to his, and there are many, many people who are working on his work. There is Frankenstein. There is also Monica Mesquita, who did her PhD with Uida D'Ambrosio, but also with Sarah Stivo on street mathematics. Alan Bishop, I was already talking about him, his talk of 85, but there is this important publication on mathematical enculturation, and he's making the difference between mathematics with a capital M and mathematics with a small m, pointing to counting, locating, measuring, designing, playing, explaining. And I became a bit puzzled about the small m and the capital M, but this is an article I will write in my stolen hours. Most of you maybe know this publication, but I was surprised that last week there was a publication in Science, and it was on the body-based units of measures in cultural evolution. So this is one of the local mathematics, that the measuring is one of the mathematical practices that Alan Bishop is pointing to. And there was an article in Science. So why do we not write articles for Science? I thought this is an opportunity to start with. It's based on a database of 99 cultures, and it's a very nice article. And I was a bit, yeah, it's nice. And then I started to be puzzled about the small m of all these local mathematical practices, because there was also this is the research article, but there is also the perspectives on this article. And this is a comment on the article on embodying measurement. And actually the author was contacting me to asking to read his review. And what is nice in this, what is also surprising, is this comment of this, the perspective is that he is not seeing this measurement of all these local practices that diverse from one culture to the other, and not seeing as a precursor of the universal system, but as a system that just exists next to the other, and it's used in many, many, many ways. So you have to think by yourself when you are using this kind of local measurement. We have Paul Ernest, is the philosophy of mathematics education, and he started to speak about mathematics and values. And actually, I have to say it's 91 that the book was published in 91. And I would like to refer to Robert Merton, who did the same exercise for sciences, and this was in 42 that he coined so the communist universal disinterestedness and organized skepticism. I also have to say something about Merton's wife, Harriet Zuckerman. I don't know how to pronounce. It's German, I suppose. And she was the first that started to take interviews with scientists. So we have to wait until, also in the sciences, like, for example, looking at the practices. I'm referring to the work of Bruno Latour with his laboratory life, was in the 70s, that he was hired to walk around into Salt Institute and to write his laboratory life. So I was a bit puzzled, and it's a question to the audience. What is it with mathematics that we have to wait so long when it comes to all these different perspectives, this psychological, social, talking about values and so on. We have now more research also at our center. Colin Rydberg is also working on values in mathematics. We have to wait so long. I did, in 2007, I did this edited book on philosophical dimensions in mathematics education, and I did the content analysis of the Flemish curriculum, looking for the philosophy of mathematics into the curriculum. And actually, I had to say, that time it was not digitalized, so I did it manually, and it was really surprising that actually there was almost nothing. There are some places in the curriculum where you have this kind of 3 hours, and there they put something about the ontological status of mathematical objects, the beauty of mathematics, and so on, the quite traditional ideas that I have to run. We have a critique on ethnomathematics and broadening up the notion of culture, and this was done by Vital and Scotsmos. And I have to say that he's retired now. He coined the concept of critical mathematics education, and it was also to move the ethnomathematical research field, to move it a bit away from the Latin Americas to the European context. And I did also some work on ethnomathematics in the European context. What does it mean? Because if you look at the description of ethnomathematics, it's identifiable groups that are doing mathematical practice and so on, then we are all part of it. So in this sense, you can say, well, it's not really a good concept if it is a container concept that and all things fits in. Where are we now? I wanted to make a reference to Hirsch because he made the link between ontology and teaching. And it's all familiar for you. So, but it has an implication, the way the teacher is thinking about the ontology of mathematics has an implication for the teaching of mathematics, but actually it's not evidence-based, and I think it should be a nice empirical research, and I'm looking at Keith to see if we can have some evidence on that. I at one of the first European conferences, Matthew, I met you. I think it was in Poland and so on. And then I started to do these small interviews. But they were all social constructivists. And I said, Matthew, I'm a bit disappointed. I hope to find people with the absolutist ideas of mathematics and so on. And Matthew said to me, you have to go to a mathematics conference and not to a conference on math education. So this is also what... okay. We submitted a paper on explanatory proofs, and this is the paper that we will present together. So with Joachim Franz, who was doing his PhD on explanatory proofs, he was relying on the work of Steiner, but I also want to refer to the work of Gila Hanna, 1990. Can you imagine that there was already a kind of attention to the role of proof in an educational setting? And in the following proof, but I will go quickly through that because Fenner already was introducing the proof yesterday, but from the perspective of rigor. And here it's from the perspective of explanatory value of a proof. And this is the proof of that also the sum of the first n odd natural numbers. And here you have the very nicely logical speaking proof. It's the proof is certainly sound, but the question if you present this proof in a classroom, what is the proof doing with the student, so to speak? And you have an alternative. So, and this is taken from an article of Alessandro, who gives this dot diagram proof, and actually it's also similar of what Fenner was presenting yesterday. So we can discuss the rigor, but in this paper we will discuss the explanatory value of proof, which is so important in math education. There are other representations, and this proof by looking with geometrical you can find in many textbooks. And I have the impression, I'm not a teacher in mathematics, but sometimes I support students that coming to me, can you help me a bit with the mathematics? And then if I try to visualize, okay, it's a fire. It's a visual proof. Okay, it's not always working that good, but sometimes the pupils are puzzled. And then sometimes it's easier just to learn by heart, to memorize how to apply this this formula. Yeah. Okay. I will go to the final overview of the paper. What we will do. So we are looking for the empirical evidence for the concept of explanatory proof. We will use the method as presented by Benedict Leuven, Müller, and Müller-Hill, and it consists of 3 steps. is the theory formation, then is the phenomenology, it's collecting the data, and then it's looking, but it's a kind of reflection, looking at the data, going back to the theoretical formation that you have. And this is not the final step because it's a dynamic process, and you can revert the third step to the first stage. And we will investigate three kind of corpus. First of all, the textbooks from secondary school level, and then the textbooks used in undergraduate mathematics courses, and then mathematics research papers to see how the concept of explanatory proof is understood by philosophers of mathematical practice and math education researchers, or philosophy of math education researchers. So this is what we have, what has to be done. I hope, I was quite short on this part of the presentation. I hope I didn't disappoint Joachim, but at the European conference, Joachim, we will talk only about explanatory proofs. So thank you for your attention. And I prepared some questions in case there should not be questions from the audience. So I'm a bit puzzled how we, or how PMP, is dealing with the social aspect of math education. And if you have some suggestions on the empirical design of the research, I'm happy to listen to that. And also Joachim, I think so. So thank you for your input and for your attention.
Thank you. Okay.
Thank you, Karen. No, just a quick question about the beginning when you talk about the citizen, because it sounded very French to me, this idea.
Okay.
I mean, I'm not French, but I work in France. And I remember that many years ago, I talked with someone working in education and saying that, in fact, the idea of French schools is that up to the primaire, you form the citizen, and then afterwards culture comes into it, but it's later. Later on, the idea is that you have to have a citizen that will go and vote and be informed about. And I'm just, maybe it's not only France, I mean, it's true that it's not Italian, but I'm wondering whether you have something to say about that.
So for
something that get to Europe and France.
So for the people online, it's a question on the concept of citizen, combined with the notion of statistics and how we have to implement it for in context of mathematics. And Valeria was pointing to the fact that it's a kind of French culture, and she's asking if it is all around the world. We had this book that appeared a couple of weeks ago with Jim Ridgway, really concerned with civic statistics, and civic statistics is all over the world. So, and it's also reflecting the concern, or the main concern, of statistical literacy, but also of mathematical literacy. So it's pointing to the reflective citizen, the citizen that has to be able to make well-founded judgments, that has, to be able to read the newspaper with a lot of information, statistics, also mathematics sometimes. So I think it comes from this move that we had, not from the 60s. Then it was the idea that we have to build on the formation of mathematicians. But now it's a broader view, and it has to be applied, or it has to be applicable to the how to say it, to the state, to the society. And I'm looking actually for this application in mathematics education. Because it's statistics education is a forerunner in that.
Okay, we'll take two more questions. One from online. Do you believe it would benefit math education to allow more space, time for philosophy of math type questions and discussions in the classroom?
Yeah, for sure. But the problem with the curricula at schools is that everyone is fighting to have more time. For example, history. They skip history, then they skip geography, and so on. For sure, I think it's important to have some philosophical discussions on mathematics, just to know that mathematics is also kind of body of knowledge that is constructed by people and in different ways by different peoples, so that young learners not have to be frustrated on the fact that they cannot grasp this body of mathematics that is fallen from the sky, and they don't know why they have to learn it, how to apply it, and so on and so forth. So I think a kind of context and badness of this body of knowledge is, I think, quite interesting.
Thanks. And then last question to Ben.
Yeah, I was thinking about philosophy of mathematics education, the Paul Ennis's book and the online articles that he puts up. But I think other than Paul, there's very few people that would call themselves philosophers of mathematics education. A room full of people who are interested in both things. And, I don't think anyone really would call themselves like a philosopher of mathematics education. Do you think this is a label that has legs? Do you think like more people should be using it, or do you think it's just kind of a label for Paul?
Easy answer. Actually, I'm not really interested in labels, but I know that philosophers of math education are seen as a bit strange kind of researchers. And I remember when we founded the APMP in 2010, there was a discussion if philosophy of math education could be included or not. So I was applying for being a member. And for sure, I could be a member because I was one of the organizers of the fund conference. But I remember it was Jose Ferreros who said, no, because it's a huge field. And yeah, I think it's also nice to have a small group of researchers on mathematical practices that can focus on specific topics, because the field is so broad. It's so broad. But I remember the first time when I went to the conference on, for example, statistics education. That time, Carmen Batanero from Granada University was the chair of this conference and also of the international group. She said, "It's the first time that we have a philosopher. Oh, that's nice. Please join the group." So I think they are open to have philosophical reflections on the research that they are doing. The fact that philosophers of mathematical practices or mathematics in general don't call themselves philosophers of math education, yeah, it's up to the individual. It's yeah.
Lovely. Okay. Thank you.
Okay. Thank you.
So we should have some fresh coffee, and we will restart at 5:15. Thanks.
Yeah, thanks for running out of time.
You talk to us once, a couple questions.
Okay, that's great.
Actually, I thought so. I didn't suggest
I don't know, whatever. Okay, thank you everyone for coming back. Hello to everyone online. So we're gonna start our afternoon session. So we're gonna talk about explanations and aesthetics. And our first speaker is Ellen. She's gonna talk about philosophical explanation. So the floor is yours. You can use this mic.
Yeah, it should be okay.
If you're staying in this area, that's fine.
Okay, yeah. I think I'm usually okay at projecting, but if you can't hear me, let me know. Yeah, so first, thank you to the organizers, Yassine and Matthew and Keith and Brendan for organizing. I'm really excited to be here. My background is in philosophy, which I'll talk about more in a second, but I am now currently a math professor, so I unavoidably have been doing some math education stuff. So I'm excited to be here with this group and hear what you all have to say. So I'm going to be talking about mathematical explanation in the classroom. And I just mentioned this, but my perspective comes from the fact that I did my PhD in philosophy of mathematical practice, a focus on explanation and contemporary mathematics, and then immediately got a job as a math professor. So I went from studying philosophy to teaching mathematics. And so questions that I kind of want to talk about in this talk today are how my philosophical training informs my teaching and how we might be able to generalize from what I've learned in my experience to talk more about how the interplay of education and philosophy of mathematical practice might go. And then I'm specifically going to look at some of my experience working with students and think about how that might inform my philosophy or how it's changed the way that I think about explanation in particular. So that's kind of where I was coming from when I put this talk together. And it's really been an interesting experience because I find my background in philosophy is something that really inherently or kind of maybe unconsciously informs the way that I teach. And so I think it's been an interesting opportunity to look at the way that philosophy can inform pedagogy. Okay, so a quick outline. So yeah, I'm going to be looking at philosophical accounts of intramathematical explanation. That should say explanation, not exploration. My apologies. And so when I say intramathematical, it just means explanations, mathematical explanations of mathematical facts, as opposed to mathematical explanations of scientific facts. And I want to first kind of unpack some of the main tenets of my own philosophical account of explanation. I'm not going to do a whole literature survey. I'm really just going to highlight what I think is important about explanation, in particular when we're thinking about education. Then I'm going to look at some specific examples of my experiences in the classroom and how I've tried to incorporate explanation and what's happened. And then I'll close the talk by making some somewhat suggestive comments. I guess how suggestive they are depends on how much you'll agree with me. But I'm hoping that this will kind of open up a nice discussion so we can talk about the interplay of philosophy and education, specifically when it comes to explanation. So that's the plan. So let's jump into the philosophical aspects. So first, I want to go over a few aspects that really summarize my general approach to explanation. So first, I think that explanation is multifaceted and that it's difficult to pin down. So I'm a bit skeptical of being able to create a universal overarching account of explanation that really captures every specific instance of an explanation in mathematics. And sorry, I should say a little bit more. And I'm currently working on a project with Bill D'Alessandro. Along these lines, we're trying to come up with a cluster conception of explanation that allows for all of this multifacetedness. I also think that a successfully received explanation gives the receiver an epistemic advantage. That is worded vaguely and intentionally so. I'm inclined to say that this epistemic advantage is usually some form of understanding, but I think that picture is maybe a little bit difficult to cash out. And so if you have questions about it, I'm happy to answer them during the Q&A. But at the very least, I think we need to recognize that explanation is meant to play some kind of role where we're trying to put the receiver of the explanation in a epistemic or in a position of epistemic advantage. And then I also think it's really important to keep in mind that the success of an explanation is very context dependent. So it depends on who the audience is, it depends on why you're seeking out the explanation, and it depends on the background knowledge, all of these different kinds of things. I think this is really crucial in the setting of a classroom because you have to keep in mind what your students know, the different levels of knowledge of your students, and how to best present a potential explanation so that it's most likely to be received successfully. Okay, so these are all things that, again, characterize my general approach to explanation, but I want to dive a little bit deeper. So first, let's look at some questions that I think highlight the ways that philosophical accounts of explanation may be relevant to education. So first, what does an explanatory question look like? I'm going to unpack all of these in more detail in the next few slides. I also think we need to consider what forms we can find explanation in. So in philosophy, we often talk about explanatory proof, but I think we also need to open up that conversation, especially when we're thinking about education, to allow for other forms of explanation. How should an explanation be tailored to its audience? Again, it depends on the context and the background knowledge of your students. And do all mathematical phenomena have a unique explanation? I think the answer to this question is no, but again, I think it's important to consider when we're looking at which explanations present in a classroom setting. And lastly, can all mathematical phenomena be explained? So these are questions that I have thought about while I've thought about the philosophy of explanation, or mathematical explanation in particular. And I think they all are significant about how we would introduce explanation from a philosophical perspective in the classroom. So let's unpack some of these potential answers in a bit more detail. So first, in terms of the questions of explanation, I want to first acknowledge that usually in philosophy, when we talk about explanation, there's a lot of emphasis on why questions. So an explanation is sometimes thought of as simply the answer to a why question. And an answer that simple is problematic for several reasons, but usually that's kind of the starting place when we're thinking about what an explanation is in philosophy. And I think that this is kind of a flawed starting place, and instead propose that we should be asking what's going on here. And maybe this difference doesn't seem so substantial, but I think it is quite a substantial difference, because I think you can ask the what's going on here question in a more meaningful way than you can ask why questions. And I also think that it better captures what we're really going through cognitively when we're looking for an explanation. So if you think about an instance when you were learning mathematics and you were just really lost and confused and had no idea what was going on, and you wanted some kind of explanation for maybe the theorem that's on the board or the fact that was just presented to you, you're usually not going to ask why. You're asking a much broader question about what's going on. Where is this situated in the conceptual space, and kind of what situates it there? So I think the what's going on here question better captures what we're looking for when we're looking for explanation. And I think that this is also useful in the classroom setting because it can help you recognize when a student is in need of explanation. So I think students are often not going to ask a why question as well. I mean, sometimes students ask why, but usually they express this confusion or this what's going on here kind of attitude. So again, I think it's a nice marker of a need for explanation. Okay, so to answer the next question that I had of what forms of explanation are there, again, proof is the one that's emphasized most often in the philosophical literature, and I definitely agree that proofs can be explanatory, But I think we also need to look other places in mathematics to find explanation. So I've proposed that definitions can be explanatory. And in fact, I think when you're first introducing someone to a new concept, definitions do a lot of explanatory work. Diagrams, I think, also can be explanatory, whether they're in a proof or independent of a proof. I think that this is a kind of a common phenomena. We often look to visualize different concepts, in particular, difficult concepts, to better grasp them. And I think that's kind of a form of an explanatory diagram. So in particular, I like to think about the stereographic projection for representing complex numbers. I think that that image really nicely captures that difficult concept and helps you reason about complex numbers and their nature. And I would argue it was explanatory. And the last category that I've listed here is counterexamples. I'll talk about these more a little bit later in the talk. But I think that creating counterexamples and being aware of the significance of counterexamples can often be explanatory as well. So I'll return to this example a little bit later, but if we think historically about examples of continuous functions that are nowhere differentiable, there were really significant counterexamples for the development of mathematics. And I think they provide an explanation about the relationship between continuity and differentiability that we otherwise kind of didn't have an understanding of before these counterexamples were constructed. Okay, so these are 4 forms of explanation, but I want to emphasize, I don't think this is a comprehensive list. In some sense, I think perhaps any kind of mathematical thing, for lack of a better word, might provide an explanation. So I really want to emphasize that when we're looking for explanation, we have to look past just proof and look at different vehicles for representing mathematical concepts and ideas. Yeah, and so I say here the value is in representing the diverse ways that we can find explanation in mathematics. And again, this is really crucial, I think, in the classroom when, especially if you're teaching a lower level math class, you're not going to be expected to be presenting proofs to your students. And you wouldn't want to say that you can't provide them with explanation if you're not talking about proof. So it's good to be aware of. All right, so the next component I want to talk about in terms of my philosophical views on explanation is degrees of explanation. So I think it's important to recognize that explanations come in different degrees. You can have deeper explanations, more superficial explanations. But I think it's also important to recognize that though we have this depth, it's not just a linear depth where you're going from a superficial explanation to deeper and deeper explanations. But I think instead it's possible that the explanations for some phenomena or phenomenon may form a tree. So that perhaps you have an explanation from one domain that forms one branch of the tree, and then a completely different explanation from a different domain that creates a new branch. And on both of those branches, you may have different levels of depth. Maybe you don't. But I think it's important to recognize that different results and phenomenon can have multiple examples, and that these multiple examples can be related to each other in a somewhat complex way, and perhaps aren't really related to each other than being explanations of the same result or phenomenon. Yeah. Again, here, I'm just going to quickly go through these aspects of philosophical explanation that I accept. If you have questions or disagreements, I definitely am happy to take them in the talk. But I want to try to make sure that I have time to talk about the classroom as well. All right, so the last aspect I want to talk about is the limits of explanation. And I think it's an interesting question to ask, does every mathematical phenomenon or result have an explanation? And I suppose that if you accept the principle of sufficient reason, you'd say yes, for sure. And I'm inclined to say yes as well. But I think it's something that's important to think about, and that it's important to think about in terms of our epistemic limitations as well. Because even if you think that every phenomenon or result has an explanation, I think we have to acknowledge that we may not be aware of that explanation. Not just because of our own limited knowledge, but because of the current state of mathematical knowledge as a whole. And so we have to recognize that we may not have access to an explanation, even if one does exist in theory. And again, this brings up an important point in the classroom, because if we think about our classroom knowledge or the background knowledge of our students, then we know that that knowledge is a subset of all mathematical knowledge. In fact, we all have a subset of all mathematical knowledge. But it's important to recognize this in the classroom setting, because you have to think about what explanations your students are prepared to receive. And you have to think about setting those students up to receive explanations when they move on in their mathematical progression. So I'll talk about this a little bit more later, but you want to make sure that you're presenting students with explanations that are compatible with what they'll learn in the future. So in a second, I'm going to talk about the example of taking the square root of a negative number, but this is a somewhat salient example because, at least in the United States, I think it's fairly common to say that it's impossible to take the square root of a negative number, which is misleading and arguably, well, false. So the idea is that when students are learning about square roots, the only information they have, or the only knowledge they have, is of the real numbers. And so it's, of course, correct to say that the square root of a negative number is not a real number, but saying that is very different from saying it's impossible to take the square root of a negative number. And the way that you present students with this idea greatly affects their success down the road. Because if students learn that it's impossible to take the square root of a negative number and then are introduced to the complex numbers, they tend to panic a little bit. Because now this impossible thing becomes possible, and it becomes possible in a somewhat bizarre way. And so it's important to keep in mind the, I guess, degrees of explanations, but also the limitations that your students have to receive explanations, and make sure that you're not harming their future education. Sorry, I should have hit enter a little while ago. But yeah, that's essentially what I say here. I think this becomes particularly important when you're doing introductory level math courses, just because, again, you're not quite sure where those students are going to take their mathematical education, and you don't want to set them up with more difficulties than necessary. All right. So to kind of summarize how I think philosophy fits into education, or my approach to education at least, I give explanation a high priority in my classroom. I encourage students to ask explanatory questions, and I often prompt students to answer explanatory questions that I pose to them. I mean, in some sense, this is just similar to the Socratic kind of style of teaching, where when students are encouraged to ask questions, they're usually asking questions that will prompt an explanation. But I think it's important to recognize that that's what's resulting from that process. So what you're really doing there is seeking out explanation, giving students an opportunity to interact with different explanations. Kind of along the lines of degrees of explanations, I like to be sure to present students with different modes of thinking. And again, this has been brought up several times in this conference already, but we know that students respond to ideas and representations in different ways. And so the more representations or explanations that a student is presented with, the more likely that they'll find one that they're happy with. And then I also want to encourage students to build conceptual frameworks that they're able to recognize and appreciate explanations that kind of relate to different domains of mathematics. Where domains of mathematics, I mean kind of loosely, where I'm kind of just looking to see them relate concepts that they wouldn't necessarily put together intuitively. Okay, so I think that my kind of views about degrees of explanation, about the questions of explanation, and the forms of explanation kind of set me up nicely to apply explanation in my classroom in this kind of way. But what I want to do now is I want to talk about how this has actually gone in my classroom. So again, I'm full-time teaching math now, and so I have lots of opportunities to introduce explanation in the classroom. And as you might imagine, it doesn't always go quite as nicely as I would like it to. But before I jump into some examples, I want to have a little bit of a disclaimer. So my experience teaching mathematics has been at the college level, but it's been a bit unique because I don't teach mathematics majors. So I teach students who take developmental or foundational math courses. So they're learning numeracy, basic function work, quadratic functions, and things like this. And so they're kind of a unique kind of classroom because not only are they general education classes, they're also perhaps a lower level math class than you would expect for a college student. And so I think it's important to note because, again, not teaching mathematics to potential, well, I guess they're potential mathematicians, but I'm not teaching mathematics to students who already know that they're on the mathematics track, doing the math major with a strong background in mathematics. And so I think that makes the role that explanation plays kind of interesting because I think in some sense, the students tend to be a bit more hesitant to explanation or maybe care less about explanation. But I think there still is a lot of value in that explanation when they do receive those and are open to them. Okay, yeah, so that's my disclaimer. I also want to emphasize that the examples I present were not a rigorous empirical study. They're just examples from the classroom that stood out to me. I would like to in the future kind of turn some of this into a more rigorous study to see what students identify as explanatory, but I just haven't had the time or the chance to do that yet. So the first example I want to talk about is one that I already mentioned, and it has to do with the square root of a negative number. So when I teach my college algebra course, we talk about complex numbers. We talk about them in connection with quadratic functions and radical functions in order to account for the fact that negative numbers are not in the domain of the square root function, at least when it's defined on the real numbers. So I ask students when we talk about complex numbers, why isn't the square root of -1 a real number? And I won't give away the answer yet, but what I hear from students is because the 1 is negative. I mean, that's true. Yeah, it's not super informative, but it's true the 1 is negative, and it's true that that's where the problem's coming from. But here, when students give this answer, they're really just repeating my question, right? They aren't giving us a real answer to the question. They're just pointing out that the negative is a problem. And then my least favorite answer is because math says so. It's my least favorite answer because I don't like to think of math as an authority, but yeah, so these are the most common answers that I get. And to get somebody to give the answer I'm looking for, it takes quite a bit of discussion. And in fact, most students are convinced that when they say because the 1 is negative, that they've given the answer I'm looking for. And so it's interesting because it points out that students, so the answer I'm looking for is because a negative times a negative is going to give you a positive. And so you can't find a real number that you multiply by itself to get -1. Something along those lines is what I'm looking for. But the fact that these are the answers and that they're confident in these answers suggests that they don't really know what an explanation is. They don't know what I'm looking for or the kind of answer I'm looking for. And I ask, why isn't the square root of -1 a real number? And so it's interesting, and it really surprised me, at least a bit at first, because I was expecting at least a couple of students to pick up on the idea more quickly. And my second example is a somewhat similar example. So when we define a function in the same college algebra class, we define a function as a relation for which every input has one and only one output. And then we introduce the vertical line test as a corollary. I don't use the word corollary in class, but it's a corollary that tells us when a graph represents a function. And so if you can't draw a vertical line anywhere that intersects the graph in more than one place, then you know your graph represents a function. And a question that I like to ask the students as our extra credit question on their first exam is why this vertical line test works. So why can we conclude that a graph doesn't or does represent a function when it passes the vertical line test? And the answers I get to this usually restate the vertical line test. So they say, because the line intersects the graph in two places. And I think maybe, arguably, that's a better answer than because the one is negative in the first example, but it still really is just restating the rule of the vertical line test. So what I really would want a student to say is, well, because a function has to have a unique output for every input, if a vertical line intersects it, then we found a place, vertical line intersects it in one or more than one place, might have worded that incorrectly in the last slide, then we know that there's two outputs for one input, right? So I want them to use the definition of function to understand what the vertical line test is really doing. And I think that that kind of gives an explanation of what the vertical line test is doing and why it's a corollary of the definition of function. But again, I think actually when I gave this question, I didn't get any student give the input-output answer that I was looking for. And perhaps I'm being too picky. I'm happy to hear your answers or your thoughts in the discussion. But again, I think this suggests that students aren't quite sure what an explanation is. Or at least when they're posed with these questions, they aren't prompted successfully to provide an explanation. All right. So I think these examples suggest that students don't recognize explanatory questions as such, and again, perhaps don't have a good conception of what an explanation is or what it should do in a given situation. I do want to mention the two examples that I presented do use why questions, and I did say that I like to move away from why questions, but I do think you can reword them as what's going on here in some kind of way, and perhaps that would be more likely to get the kinds of answers I want from the students. But yeah, I just want to point that out. Perhaps that's where things went wrong. Should be interesting. I also have noticed from these two examples and other examples is that students don't agree on what counts as explanatory or what they would provide as an explanation. And it seems like this disagreement is not coming from a lack of knowledge or a difference in background knowledge. It seems much more like an intuition-based disagreement. So this is a little bit less present in the two examples I presented, but to give another brief example, when I teach calculus, I introduce students to the method of doing proofs by contradiction, and I explain contradiction in kind of a way using the idea of a disjunctive syllogism. So we say A or not A, we assume A, show that it leads to something absurd, and then use that to rule out A, and therefore conclude not A. And the success of this explanation of this method really resonates with students drastically differently. So I have some students who love it, some students who are really receptive to it, and some students who hate it and think that starting from A or not A is an absurd idea in the first place. And so I think in those cases, it's not really a difference in knowledge. Perhaps it is, but I think it's less clearly a difference in knowledge and more has to do with intuitive ascriptions as to what's explanatory. And the last thing that I want to take away from these examples is that I think there may be a distinction between the kind of explanation we expect students to give or that we expect students to respond to and an explanation simpliciter. And I'm going to talk about this more in the next section, but essentially I think that perhaps what students are prepared for is some kind of introductory explanation, where maybe these are the explanations that occur at kind of the superficial or low level area of our explanatory tree, and that students aren't really ready to think about explanation more deeply until they've really conquered these low level explanations. Okay. So I now want to talk about some methods for encouraging explanation in the classroom. So we saw the two examples I gave were not super successful, but in light of those, I've tried to incorporate explanation more often in my classroom and try to present students with questions that will naturally get them to think more about mathematical explanation. So here I list computational questions and conceptual questions. I think these are two bad ways to prompt explanation. I don't think they're necessarily bad, but I think that students need a bit more introduction to explanation before they'll find explanation from these kinds of questions. So in the case of computational questions, these are kind of similar to routine tasks that Colin brought up. So cases where you're just following an algorithm and doing a methodology and maybe don't need to put much thought into it. And then conceptual questions, I think, are not always the best for prompting explanation because they're too open-ended. So I think that this maybe is kind of the place where my two example questions went wrong. Perhaps they were too open-ended and students didn't really know what they were being asked to provide. So again, I think for conceptual questions to be effective, students first have to have a good understanding of what an explanation would be. So as an alternative to computational conceptual questions, I like to put emphasis on constructive questions. And there's two kinds of constructive questions that I want to talk about. But what I mean kind of in general by constructive questions are the kinds of questions that require students to do some kind of construction work on their own, where they're maybe building an example, defining a function, finding a counterexample, something along those lines. And I think the first kind of question that successfully does this is true or false questions. So I think true and false questions where students have to explain why the statement is false if it is, really challenges students to think about counterexamples and to think about the space of possibilities that kind of lie within the conceptual framework. Hesitant to use possibilities there. But basically, students have to think about the conceptual framework and what's happening to figure out if there is a counterexample. And so an example that I particularly like is the statement, a function that is continuous on the interval a to b is also differentiable on the interval ab. And the example I mentioned earlier of continuous nowhere differentiable functions would provide a counterexample to this. So we do talk about those in a class where I would ask this question. And so students could just say no. In the 19th century, a lot of this work was happening where we found continuous nowhere differentiable functions. But I like this kind of question because students don't have to rely on that historical knowledge either. If the student was absent that day or just was zoning out and didn't remember that example, then they can still think critically about what kinds of functions have points where they aren't differentiable, right? And so the most common answer I get to this question is actually false because of the absolute value function, which I think is interesting because it allows students to kind of use what they know about non-differentiability and use what they know about functions to create, well, in some sense, create an example on their own. Okay, I know I'm running low on time, so I'm going to try to get through the last few slides quickly. The second kind of constructive question that I've made use of quite a bit is what I'm calling function building questions. Definitely not tied to any of these names. If people have suggestions, I'm happy to hear them. But students that give criteria that needs to be met to define a function or draw a graph. So something like draw the graph of a function with a domain from -5 to 4 and a range of -2 to 2 and a discontinuity at x equals 1. So these are questions that you can find in most standard calculus textbooks, but I think they're ones that really give a student or these students an opportunity to grasp the concepts that we're talking about when we talk about real valued functions. So here I just mentioned discontinuity and range and domain, but you can use this kind of question to talk about differentiability, to talk about continuity in more detail, and to talk about really any kind of properties of the functions that you want to cover. The second example I have is write an equation of a function that's a degree 2 polynomial and has a line of symmetry at x equals -2. Again, it requires the student to basically have an understanding of what these facts about the function mean graphically, and then apply that in function notation. So I think it again gives the opportunity to the student to provide an example that they come up with themselves. And so I think it's important to recognize that in these function building questions, there isn't a unique correct answer. And so the student's able to really use their own background and preferences to come up with an example. And I think that it's valuable to have students compare their answers as well to see the variety of different possible options. All right, so I do want to emphasize that constructive questions will not immediately yield explanations, but I think what they do is they allow students to think, and they allow students to think in the direction of an explanation. So if we were going to think about the relationship between continuity and differentiability, then we could use that true-false question to encourage students to start thinking about what an explanation might be. Okay, and let me see. So the last section I want to talk about was the interplay of philosophy and education. So I'm going to go really quickly through this. So I want to first emphasize that it seems like maybe there's a dilemma here. That's kind of like a chicken or the egg dilemma, where maybe we're asking, should we do math education first or philosophy first? And I think it's important to recognize that ideally we want an interplay where maybe where you start doesn't matter as long as you're taking both into consideration. And given the nature of this conference, I think we're probably in agreement with that. So we'll leave it at that, but please let me know if you disagree. I already kind of mentioned introductory explanation, so I'm going to leave this for now as well. Sorry, I know I'm almost out of time, so I want to say a little bit more about the construction is explanatory. So the last two slides about introduction and about context, I think take philosophy and say something about how we might change our pedagogical practices to incorporate some of those philosophical components. So if we think there's this distinction between introductory explanation and explanation simpliciter, maybe that changes how we present ideas in the classroom. But this last example, I think, is a way where at least my experience from education, has made me think more about my philosophy of explanation. So if it is the case that constructive questions are better at encouraging explanation from students, then I think that's an interesting comment about the philosophy of explanation. And I think it suggests that maybe when we're thinking about the epistemic advantage that explanations give us, maybe there's something similar between this constructive process and the epistemic process of receiving an explanation. And so I think that's something that would be interesting to look at in more detail. And I wouldn't want to go as far to say accept constructivism as for explanatory reasons, but I think it'd be interesting to think more about that detailed relationship. And in the interest of time, I'm going to stop there and open the floor to discussion. Right, I'm out of time. Yeah.
You can show the
Okay. So inclusions, I think students should be encouraged to pursue explanation from a philosophical point of view. I think we need to teach students what explanation is and how to seek it, because I don't think that's something that students are naturally inclined to do in the way that we might expect. And I think that philosophers should take the pedagogical process into consideration when they're theorizing about explanation. That's it. Thank you.
Thank you. Thanks for that, Ellen. I enjoyed that. I'll give a comment and then a question. So, encouraging the cross-fertilization. One of the constructs that's a famous one in mathematics education is something called a awful word, socio-mathematical norm.
Okay.
So it's norms are kind of being used to describe as regularities and expectations in the classroom. So one norm in the classroom, social norm, would be I can raise my hand before speaking, you don't put things out. And then socio-mathematical norms are kind of a mix of the social and mathematical. The theory behind this is that what counts as a justification or an explanation, those type of things in the classroom is actually a normative. So it's an expectation about what is a legitimate mathematical contribution. So I can send you the references, or if you can Google, you Google Scholar to be able to follow it as well. But the idea here is that there's sort of a social expectation that the students may be being given, and maybe in the previous experience we said why or explain that to me. That means show your work or say one other. So that's the comment. Question. I was wondering. So yeah, two related questions. Would all justifications to you count as explanations? And the other thing I was wondering with the square root of -1 example. Suppose I said to the student, well, why is the square root of -x squared not a real number? And they said to you, oh, well, -x squared is negative. Would that be an explanation?
Yeah.
I don't think we did the question
Yeah.
very quickly.
Yeah. So definitely correct me if I'm wrong. First question was, are all justifications explanations? So I'm inclined to say no. I think that there are examples of proofs that are non-explanatory. Let me see, I'm having a hard time coming up with one off the top of my head right now, but short answer is no. And I think that, I mean, I accept kind of the traditional line that explanation is a step past justification epistemically. How far past it is, I think, is a
Maybe
fuzzy thing.
elaborate on that, because it seems to me that the square root of -1 not being a real number, your explanation that you were desiring was a negative times a negative is positive.
Well,
If that would count, what would?
that would count. I see. Yeah, I mean, so I definitely am on the side where I count more things as explanations than perhaps other people do. But I think, let me think. I mean, I think there's instances where you have more complicated mathematical facts and you have brute force proofs that don't provide explanations. So I think given the context of the square root of -1, you're really asking a question about number systems. And so I think the explanation aligns somewhat with what you might think is just a pure justification because of what you're really looking for. But I think, yeah, I mean, I guess I think it's explanatory that it's impossible to multiply a number by itself and get a negative answer. But perhaps that's just an intuitive disagreement between us.
I don't disagree.
Oh, okay. Yeah, I'm sorry, I don't have any concrete examples of non-explanatory proofs off the top of my head right now. And your second question was?
Oh, yeah, so instead of the square root of -1,
Oh.
So square root of -x squared. I
Yeah.
was thinking you might count that because it's adding a little bit more that might be on the definition.
Yes.
Curious as to what you were thinking.
Yeah, that's exactly what I was thinking. So the question was, would I think the square root of -x squared, if they gave the same because x squared is negative answer, if that would be explanatory? And I think yes, it would, because it moves kind of out of that numeracy domain where now you're asking more about functions, and you can say -x squared is a function whose range is always non-positive, or yeah, non-positive. Yeah.
Yeah, thanks. You said something almost as a throwaway in the middle of that. I just wanted to ask you about it.
Oh,
You said
yeah.
you think every mathematical phenomenon has an explanation.
Yeah.
I just well, firstly, I'm just curious as to what your rationale for saying that is, and then maybe I'll press you on an example, which
Okay.
I've just never come up with an explanation for.
Yeah, okay. So question was, why do I think that every mathematical phenomena has an explanation? And I mean, the brief answer is that I'm an optimist.
Okay.
I mean, I think it's also because my claim isn't that we have an explanation that we're aware of currently. I just think it's possible, in theory, to come up with an explanation for, and maybe it's coming from the philosophy in me being so ingrained with the principle of sufficient reason, which says that every phenomena has an explanation. But
so let me just give you an example which cropped up when we're interviewing for new lecturers in this department, and what happens is we bring them in and they do a fake lecture, and people ask them questions pretending to be students. And this was a stats lecture, and I said to this person, why is the critical value, the 5% critical value of the t-distribution 1.96? And this completely threw this person.
Yeah.
And after they went out and we had this discussion about this. And I said, actually, it's a completely unreasonable question. There's no good answer to that. and a mathematical focus. No, there is a good answer. The explanation for that is that it's the area under the leadership.
Yeah.
So that's just restating the question.
Yeah.
You know, and I occasionally there's no explanation for that. That's just the numerical answer.
Yeah.
Do you disagree?
I mean, I'm inclined to accept the area explanation as an explanation.
Okay.
Maybe with a bit more fleshing out, but I mean, because I think in general, if you're going to ask it with less specificity, what a word, then you'd give something like an area explanation for, in general, how do we get Z-scores?
Yeah, but why is it
Perfect.
1.96?
Well, yeah, I don't know. Yeah, the area. I don't know. I'd have to think about it more. I mean, so I'm still inclined to say there's an explanation out there. I think maybe it's going back to kind of Keith's worry as well, where maybe my bar for what counts as an explanation is too low, but I'm happy with it.
Oh, yeah, I really like this. I was thinking about the on-take epistemic distinction for explanations.
Yeah.
I guess coming in, I was expecting to see lots of epistemic stuff because we were going to talk about the classroom, but some of what you said didn't gel so well with that, especially the degrees of explanation and the tree-like ordering. That seemed like something that looks very on-take to me. Some, structured relation between the explanation. Were you thinking of it as mostly epistemic, or?
Yeah. So yeah. Yeah. So I definitely think of it as epistemic, and even when I talk about the trees, I don't mean it in an ontological sense. I can see where, I mean, it's an order and it gives structure, like you're saying, but I really mean in terms of epistemic depth. So you're getting explanations that have more epistemic complexity. So I was thinking of it on a epistemological scale, but maybe you're skeptical that it's possible to do that.
Yeah, maybe. I can maybe see that they're more complicated or less complicated. But,
yeah. But I mean, I also want to say that a lot of explanations build on one another, right? So you can give an explanation of a fact in a college algebra class that doesn't involve any group theory, and then explain it using group theory, but really with the same kind of maybe idea, the same essence, for lack of a better word. There I go with ontology again. So that's really what I mean, is you're kind of, it's interesting. Yeah, I'd have to think about it more. But I mean for it to be epistemic. Maybe it's a bad way of presenting that. Yeah, thank you.
Yeah, that's a good question, Mike. So in the classroom, I think, so when you ask for explanations from the students, it seems like this might be very complex when you understand what an explanation is. So it looks like you want to use Einsteinian type, but they have to learn the language game of providing explanations. And explanation. Even here, we also see that even between you, it was hard to figure out what's the explanation or what's not. My question is, so do you think that there's some kind of an extra layer of first, we should first teach the game so that they understand what is expected from explanations before doing it on the specific content, or do you think that it has to be integrated and you have to do that on in situ, so to speak? Directly with that?
Good. So the question is, should we introduce explanation first, or should we introduce it kind of in an integrated way to familiarize students with it? I mean, it's a tough question. If I had all the time in the world, I definitely would want to teach it first, with a lot of emphasis on it, kind of in why we care about it. I mean, I think in general, students lack an appreciation or understanding of what mathematical reasoning is and the exact nature of even just low-level epistemology of math. And so I think it would be valuable to spend some time looking at those kinds of issues. And I think students might be more able to get more out of those kinds of answers. But I think practically speaking, I mean, I think it's tough. I think that in some sense, we all have an intuitive understanding of what explanation is. And so I guess my initial impression was that you could say, give me an explanation for this fact. And if I asked you to explain to me why you decided to walk to campus today instead of take the bus, you probably can answer that question in a coherent way. And so I was thinking that mathematical explanation would be somewhat similar to that, and that students be able to grasp it in that sense and maybe get more sophisticated as we moved on. But I think, yeah, that in order to do it properly, you do need to spend the time to really think about at least a loose understanding what explanation is before you ask them to provide them. Does that answer your question?
Oh, yeah. Okay.
Yeah. Okay.
Yes. So there's I think a couple of questions online, and then you can answer. Do you think it might be worthwhile to think of explanation more broadly than in maths, for example, to contrast mathematical and scientific or psychological explanations? Then there is are you satisfied with explanations of the Riemann hypothesis, not just of why it should be true, but even what it's saying?
So in terms of comparing mathematical and scientific explanation, the question was, do I think that's worthwhile?
Yeah, so would it be interesting for us to contrast them for them to understand what's going on in mathematics?
Yeah, I mean, I think in some ways yes, and in some ways no. So in scientific explanation, there's usually so much emphasis on causation and dependence and ontology. I like to kind of try to move away from that discussion in mathematics because I don't think there's mathematical causation, and I'm not so interested in dependence relations. So I think to some extent, yes, and to some extent, no. I think it would be really nice if the way that we think about explanation in mathematics generalized to science more broadly, but I'm a little bit skeptical about that possibility. And second question was?
That's about the Riemann hypothesis, but I'm not sure. So are you satisfied with explanations of the Riemann hypothesis?
I'm not familiar with any. Sorry, I didn't study up.
So you said fairly early on that you want, rather than what is,
Yeah.
rather than why questions, the invitation for an explanation, your preferred form of words was, what is going on here?
Yeah.
And I turned that over for a bit, and it strikes me that you can ask that question without being in any position to characterize, grasp, describe, or name the explanandum. Right? So you come upon some scene and you don't know whether it's a road accident or a demonstration or the result of a storm. Right?
Yeah.
So you have no idea what it is that you want to explain, but you just know there's something out of the ordinary. So that seems to me to be importantly different from the circumstance where you are able to quite precisely indicate some phenomenon and ask why is that the case?
Yeah.
And I find myself, I kind of,
yeah.
I'm in favour of things being loosened up and clusterified and so on. But I can't help wondering whether you've kind of overloosed that form of
too
word.
much. Well,
leave things so loose that maybe that connects with your willingness to regard things as explanations that.
But the worry in the accident case is that there's not enough it's not specific enough.
Yeah, that you can say what is going on here in more or less any circumstance.
Yeah.
Like
but what if you take here?
You might personally be in the midst of a psychotic episode, and you could reason. What is going on here? Would be a reasonable thing for you to say.
I guess what if you thought about here as a variable term where you have to fill in the specific? So like if I said what's going on, and we take the square root of -1. That's really what I mean.
Right.
So I think of here as being. It's just that it's hard. I guess I could have said what's going on X or what's going on with X, but that's really what I mean. So I imagine that maybe your first intuition is to ask that general what's going on here question, but that usually you can specify it to say what's going on with this particular phenomenon, which is really what I mean.
Oh, so I was overreading.
Yeah, right. That was a fair point. Yeah.
Okay, so I think we're going to close now. Thank you very much. So we convene for 5-10 minutes.
I kind of think of his staff away. So.
then we start sharing.
So I know it's already shared.
Oh, sorry. Sorry.
No,
Oh, I messed it up.
I can.
Sorry.
Sorry.
So close to doing it right.
We were gonna get there. I'm convinced. Confident. No worry. What do we see?
And now you also see us.
Like if you stand in front of the camera, yes.
Is that okay? Because I don't see.
Yeah, that's fine. And the sound.
Okay. Should I say hide here? Yeah.
I can introduce you, don't worry. I'm gonna introduce you.
I can hide that.
Okay, then we can. Okay.
Yeah, we should start.
It's fine.
but we're
Okay.
already
So,
not
don't
started.
worry, I'm going to continue. So, we're going to go with the next talks on the explanations. And so, this is Celia Petofoli from Pavia, and she's going to talk about what explanations can be. The floor is yours.
Or cannot be, in fact.
Cannot
But
Sorry.
can be actually. So it's gonna be just a talk on mathematical explanation. I want to start with a disclaimer. So I started to work on this topic really recently, and I think I'm very grateful to Pablo Maya Ramos, who invited me just a few weeks ago at Rutgers. He organized a conference on mathematical explanation with philosophers and math education people, and he asked me to discuss there. And I thought, it's great. I just go there, ask a few questions. So I didn't know that actually he planned a whole hour for me to actually engage with the material of the conference. I had to start reading a bunch of papers, etc. And so I think just that episode shows, from my perspective, that there can be really good interaction between the two communities, and at least like it made me work on something I didn't work before. So that's interesting. But today I want to present some kind of limitative results and some dangers also related to interdisciplinary studies. That's why the title a bit negative, what mathematical explanation cannot be. So let me start with a little bit of introduction on the interaction between philosophy of mathematical practice and math education. So first of all, I want to say that it seems to me absolutely natural that there can be a fruitful interaction. So recently, Becky Morris and Yasin Amami have been written about that, and Yasin has a draft that some of you already mentioned. And I think like philosophy of mathematical practice is really looking at mathematics from the perspective of the agents, the working mathematicians, also the students. So it seems like obvious. We are asking kind of same question using a little bit of different methodology, but I think it's a good thing to start a more systematic dialogue. But what I want to say is also that interdisciplinary research is also very hard. Like it can be fruitful, but it's, I think, harder than we think. And it's not enough just to talk a little bit about things, but we have to kind of get clear on the terms of the debate. And I think there are some problems in doing that. So the problem I'm going to focus on today, it's about using the same words to refer to different phenomena. Yesterday, Tanner Townswell talked about proofs, and in particular on the difference between proof presentations and proofs, and when are two presentations presenting the same proof and when not, so criteria of identity of proof. And just to talk about this stuff, a lot of kind of philosophical background is presupposed. And I think in the math education side of things, sometimes the term proof is equated to the one of proof presentation. And I've been thinking and talking about this also with Matthew. We have an ongoing discussion. But I started to think more about this when I talked with Marcus Giaquinto. Actually, that's not 2015, it's 2016. I gave a talk at a conference in Croatia, and he was criticizing actually a result in mathematical education by Inglis, Meyer, Ramos, Weber, and Alcoca from 2013, in which an empirical study was used to show that there was a lot of disagreement among mathematicians regarding whether a certain argument is a valid proof or not. And according to Giaquinto, there was a problem with the methodology of this study. There was a confusion between proofs and proof presentations. So the author of the studies were presenting an argument and calling it proof, but in fact, according to Giaquinta, the mathematicians were evaluating the presentation. And so Giaquinta was not against this study. He thought that's actually really super interesting. The problem is like how we should interpret this study and what categories we should use. And so kind of the moral he gave is that the empirical claim justifies only moderate conclusion, not the strong conclusion that appeared in the paper. And I think this is very similar to something actually that Yasin was saying today in the Q&A after Keith's talk. So what actually are these experiments showing us? So today I'm going to focus on mathematical explanation and show that, or I think that it's an ambiguous expression and it's used in different ways. And I think this is actually a problem in the literature. And here, what do I mean? First of mathematical explanation, just to give you a broad sense. We already hear from Ellen now. So we are thinking of something in which the explanans is mathematical, but in this particular case, we also think of the explanandum to be mathematical. So some people call this intra-mathematical explanations. So mathematical explanations of mathematical facts. Okay. So just a last preliminary slide. I think explanation is a kind of very important topic now in the philosophy of mathematics. And it's also a success story for the philosophy of mathematical practice. In fact, the philosophy of mathematical practice is gaining traction in the literature, but it's still kind of a marginal part of philosophy of mathematics, or maybe not, I don't know. But Leon Orsten, for instance, in the Semper Encyclopedia article of philosophy on philosophy of mathematics, he puts philosophy of mathematical practice under the future as something that has yet to be developed. But I think, in fact, the case of mathematical explanation is really a case of success. The areas become one of the most widely discussed by analytic philosophers of mathematics. And in fact, it has important ramification in general philosophy of science as well as in metaphysics. So there is all the issue of metaphysical explanation and grounding that is supposedly connected with the one of mathematical explanation. So it's really central from the point of view of analytic philosophy. But of course, the topic of mathematical explanation, it's also very central for mathematical education. So we heard the talk today, but also before by Karen. She mentioned a co-author work she has on the topic. My question is, are we really talking about the same phenomenon? And my answer is going to be no. Actually, I think we are going to talk about different things. Related, to be sure, but different. Moreover, just another thing to say is that there are also psychological studies on explanation. In the Rate conference, there was Tania Lombroso, a very prominent psychologist, but there are not so many psychological studies on specifically mathematical explanation. So that would be also something to look out for in the future. So here is a quick example by Mark Lang that I'm going to go very quickly because I have a lot of material and not so much time. But probably all of you are familiar already with this. And this gives us also a good example of non-explanatory proof that Ellen was also agreeing that there are proofs that are not explanatory. So here you have the definition of calculator number. You take it's a 6-digit number that you can take by taking 3 digits on any row, column, or main diagonal of the keyboard. So for instance, 753 357 or 123 321, etc., like a 6-digit number of that kind. So it turns out every calculator number is divisible by 37. That's weird. Like it seems like, oh, it's a coincidence, or like, why is that so? So it invites an explanation. Like, we are curious about it. There's a sort of surprising fact we want to explain. Why is this true? You know, there are not so many calculator numbers. We can just check one by one. We are gonna prove that all of them are gonna be divisible by 37. That's, I think, a prototypical example of a non-explanatory proof. We can be very convinced that the claim is correct, but have no intuition whatsoever of why this is the case. So we want something more. And so this is an example, in fact, Mark used to show that instead this other proof gives us such an explanation. So all the calculator numbers can be written, are formed by three integers, a plus d, and a plus 2d in arithmetic progression. And so we can just write them with the powers of 10, 10 to the 5, a, 10 to the 4, a plus d, 10 to the 3, a plus 2d, and then go back, a plus 2d, plus 10, a plus d, plus a. And then simply doing some manipulation, we regroup, and we find that they are all 3 times 11 times 37, etc. So they are all divisible by 37, and it seems like this is a more general type of reasoning that allows us to explain this surprising fact, which is not done by the brute force proof. Okay, just to give a simple case. So here, I'm going to give you a lot of material, but I'm going to go a little bit quickly just to give you an idea of the views on offer. And since I was just at this math explanation conference at Rutgers, I'm going to talk just very briefly about what were the proposals there. So Mark Lang has emphasized in a series of papers and also in his book on non-causal explanation that salience is really what we should look for when we look at mathematical explanations. And he says that explanatory proofs exploit a certain kind of feature in the problem, the same kind of feature that is outstanding in the result being explained. And so for him, it's really important that not everything admits of an explanation. So in some cases, it doesn't make sense to ask for an explanation. There's not like a deep explanation of why 5 plus 5 equals to 10. That's a simple computation. But there is an explanation of the fact that all calculators' numbers are divisible by 37, because that's something that strikes us as weird. Like, we just want to ask, why is this the case? And he emphasized like the importance of symmetry, unity, and simplicity in his account. Then we have Bill D'Alessandro and Ellen. They're working together on a views according to which to possess an explanation of some fact is to be an appropriate state of understanding with respect to that fact. And then they do some work to divide between objectual and explanatory understanding. I'm not going to go into the details. Then we have Katerina Dutil-Nova's account in which she has a dialogical account of proofs. And in her words, she says, persuasion and explanation go hand in hand in mathematical proof. A proof will be more persuasive precisely if it's viewed as more explanatory. So persuasion and explanatory go together. And then Jessica Carter was also presenting, and she had a view on explanation focused on understanding. And a view based on case studies rather than general principles. Okay, these were the philosopher side, which I'm more familiar with. Here are quickly also the math education side. So Pablo was presenting some of the results. He did some empirical studies with a mathematician and tried to answer the question, what do mathematicians think about explanation? And I'm gonna talk in details later about this. I'm gonna be quick now. Or do mathematicians write about explanations? So he did a very interesting corpus analysis to search for words like explanation, explaining why, etc., in mathematical papers actually published. And he found out that actually mathematicians talk very little about explanations, even compared with physicists, say. And that's interesting. And then we had Bethany Ritter Johnson. She thought of explanation as things that provide answer to why and how questions. And she said that explanations are linked to the process of trying to figure things out. So try to understand. Megan Staples was defined explanation as something making plain. And offering an explanation for her was offering their understanding. So clearly the link between explanation and understanding was very strong. And then Tania Lombroso, she proposed a functional account actually to causal explanation. So that's a bit different from the psychology side. So all these accounts are super heterogeneous. And I thought, actually, after the conference, at the end of the conference, I gave a general commentary with Keith Weber here on all these views. And we thought actually it would be nice to distinguish between two different ways the term explanation is used. And so just to take inspiration from Kahneman, system 1 and system 2, why don't we have explanation 1 and explanation 2? In some sense, they track the two systems, actually, as you will see. So, but first, like a couple of words on understanding and explanation. So it seems understanding plays a crucial role in all views presented at the Rutgers conference, except for Lang. So Lang's view allows for the fact that understanding generally, explanation generally generate understanding, but it's not constitutive in its view of explanation. A general worry connected to linking explanation to understanding is the risk of overgeneralizing. What is the phenomenon we are trying to get at? Are all justification explanation? It seems like no. These are potential problems. Actually, scholars, also from the math education side, everyone seems to be aware of this. Or maybe not everybody, but like the people who engage in this interdisciplinary discussion. For instance, Pablo and Evans Rittenberg in English, in a recent paper, they say, outside of the philosophy of mathematics, mathematical explanation is frequently interpreted in a pedagogical sense, especially in the math education. We're talking about pedagogy, after all. Mathematical explanations are the kind of things that someone may say or do to help someone else grasp a mathematical idea. So they are very clear that the way mathematical explanation is used in the philosophy of mathematics is different compared to the way it's used in other contexts. So they accept this. Same in a 2005, so really at the dawn of the talk of mathematical explanation, Apner and Mancuso were very clear about that as well. So I'm not going to read all the quotes for the sake of time, but basically they say explanation is an ambiguous term. It admits we can explain the rules of a calculus, etc. But then they say there are deeper uses of explanation in mathematics which call for an account of the mathematical facts themselves, the reason why. And so they divide between instructions and genuine, what they call genuine mathematical explanations. Okay, so here's the proposal. We came up with this. It's approximately, it's just like a tentative way to make order here in the literature. Explanation 1 would be something vague, more general, looser, an answer to a why or how question that enhances understanding. That's a characterization. And I think this is what people in the math education literature are generally trying to get at. Certainly Ellen seems in her way of talking about her interaction with students. That's something she wants to get at this kind of thing. And the second one is like a technical, philosophical term. It's a scientific explanation in which both explanandum and explanans are mathematical. And it can be characterized as an answer to a why question. Okay, so just to give you a better sense, especially for the non-philosopher here, of what explanation 2 might be, I took some insight from a recent book by Pincock from 2023, in which he gives a few basically axioms of explanation, like what all accounts of explanation must satisfy just to be explanation. And he says, 1, there is an important distinction between a description of some target of explanation and an explanation of the target. So description and explanation, not the same thing. These are his words. A legitimate explanation of a target indicates why the target is the way it is. It's not just describing the target. Second, very important, there's an important distinction between the evidence for some fact, so the justification for a fact, and the explanation of that fact. Really key. We should ask, what are we asking our students when we ask for explanations? Sometimes I think we just ask for evidence for a fact. He gives an example. Careful paleontological investigation may determine that the rate of the Earth's rotation on its axis is decreasing, but additional account of the gravitational interaction between the Earth and the Moon are needed to explain this change. So evidence alone is not sufficient. And third, priority. If A is a part of an explanation of B, then B is not a part of an explanation of A. So this seems like what explains something else is in some sense more basic or fundamental. There is an asymmetry in the explanatory relations. Okay, and I think part 2, it's really key to distinguish between explanation 1 and explanation 2, because explanation 1, I think, includes maybe all sort of evidence, also something that's normally not allowed in accounts of scientific explanation. So this is something that should hold also for scientific explanation. And just to give you a sense of the symmetry constraint or asymmetry constraint on explanation, this is a very famous example in the philosophy of science literature. It's a counterexample to the Hempel covering law account of explanation. That was one of the first accounts of explanation that was proposed. And the idea here is that we have a flagpole, we're in the beach or wherever, we have a flagpole, and the flagpole casts a shadow. We ask, why is the shadow 2 meters long? So we ask an explanation for why is the shadow 2 meters long. And following Hempel's account, we appeal to some general laws, in this case, laws of trigonometry, to the laws of the light ray goes straight, and to a specific fact that is the length of the flagpole. So we explain why is the shadow that long by appealing to the general law and to the length of the pole, right? So the counterexample is because we can do precisely the reverse in a way that seems weird, because we can also ask, why is the flagpole 2 meters long? And by the same consideration, we can appeal to the general laws and to length of the shadow to say, it's because the shadow was this amount of meters, and the trigonometry works that way, that the flagpole is that long. And we certainly, that's evidence that the flagpole was that long, but it doesn't explain why the flagpole was that long. Probably the flagpole was that long because the guy who built it wanted to have it that long, or he had instruction to have it that long. So that's an example of something that's evidence, but it's not an explanation in the scientific sense, or in the explanation 2 sense. So to return here, we have Mark Lang approach. Certainly he wants to, I got it wrong. Certainly he wants explanation 2. I got them all wrong because the other one. So he wants explanation 2, but Katerina Dutinovas and Jessica Carter are certainly looking at explanation 1. I'm so sorry for now you take picture of my wrong slides. I'm sorry. But the idea is also Katerina has this account in which explanation is something that allows to convince other people. That's clearly not explanation 2. Sorry. And for D'Alessandro and Late project, I'm not sure. Actually, for the noeticism, because I talked with Bill and he wants to have a kind of more continuity with philosophy of science. So he wants to go at the explanation 2, but I'm not sure. And what about the math education side? So these are correct. So now the names are correct. So they, like Bethany and Megan, certainly want explanation 1. They are really explicit about that as well. Tanya, she said explanation 1.5. But she has a background in philosophy. She studied a lot of philosophy of science, and she wants to get at that kind of phenomenon, but kind of losing it up a bit to include the explanation for children and things like that. But definitely she's focused on a why question, certainly not how question. And Pablo, I don't know, we'll see. So then my question is that, is mathematical explanation like explanation 2 a real phenomenon, or maybe not, in fact? So mathematical explanation 2 is connected to a why question generally. But still, we are looking at finding accounts from the bottom, like a bottom-up approach in which we look at specific instances of explanatory proofs or other explanatory things. And one could ask, are these results generalizable at all? And I think that even a pluralistic account that showed that explanation is a multifaceted phenomenon, as Ellen was emphasizing, must give us some general claims as well to be an account of explanation, or to show that explanation is actually a phenomenon worthy of philosophical theorizing. Pincock again says, all participants in this debate agree that a scientific explanation provides a reason why something is the case. And then there are obviously like a lot of differences on different proposals how we should understand these things. So I focus on explanatory proof because I think like that's a prototypical example. There are other things that are explanatory, but I think the difference between explanation 1 and 2 is really clear for the explanatory proof. So understanding how the proof supports its conclusion, that's explanation 1. So that's just understanding why that's a good evidence. But explanation 2, it's really related to understand why the conclusion holds. So here in a previous study, Inglis and Aberdeen found that explanatory had moderately loadings on the utility and precision factors and a moderately negative loading on the intricacy factor. In other words, proofs were likely to be rated as explanatory if they were seen as useful, precise, and non-intricate. That's clearly explanation 1. So that's clearly like good mathematical, proofs that were clear, that gave us a clear sense of how they supported their conclusion at a high grading in the explanation factors. So that seems explanation 1. Also, we have scholars that emphasize the connection between explanation and visualization. Common observation that visual proofs are often explanatory. And this is also something that is predicted by the functional account of Meyer, Ramos, and Inglis that links explanation to understanding. But again, I think some proofs can be very convincing without explaining why the result is true. And the visualization aspect is exactly connected to the being convincing aspect. And here I'm gonna just skip this Steiner quote. And I want to say, so that studying mathematical understanding, I think it's very interesting in its own. I also spent so much time to studying how visualization, for instance, enhance understanding. I just don't see why we should connect it to the debate of mathematical explanation at all. I think there are different debates, but I don't think one is more important than the other. I think they are different. So we just heard about Ellen's proposal on substituting the why question to a what's going on here question. And she does that precisely to emphasize the connection between explanation and understanding. So I'm just skip this because we just heard it. So she says, the crux of my criticism of this why question framework is that it does not capture all that there is to mathematical explanation. I totally agree that it does not capture all that there is to explanation 1. Certainly doesn't. But it seems it does capture the thing that about explanation 2, by definition almost. Again, I want to emphasize that the what's going on here question is a very important question to ask. And to me, like the way I see it, just corresponds to our drive or search for understanding. That's what drives mathematical discovery. And that's maybe like the main aim of mathematics, according to some people, mathematical understanding. And she has examples, like she mentioned before, also like this example of continuous nowhere differentiable curves in which there is not a specific why question, but a what's going on question. What's going on here question allows us to develop an understanding of the real numbers and function depends on them. Great. In fact, like we want to have more mathematical understanding. My question is, why do we need to call it explanation? In fact, she explicitly say what we are really interested in when we see, she said, when we seek a mathematical explanation is to develop understanding by means of developing familiarity with the relevant mathematics. So that is just understanding. And there could be very important type of understanding, for instance, how an argument supports its conclusion that has nothing to do with the explanatory phenomenon studied in the philosophy of science. The same difference holds in philosophy of science as well. Like we have that explanation 1 also in philosophy of science, of course. And this also kind of broadening the term of explanation also brings new things into the domain of the explanatory. She mentioned explanatory definitions and even explanatory diagrams. Again, this is very interesting very interesting, but it's not clear to me how it connects to the topic of explanation 2. I don't even know what does it mean for a diagram to be explanatory. I love diagrams, and I think, again, they enhance understanding, and they can really give us a clear grasp of arguments, etc. But I just don't see the connection here. And I'm afraid that this kind of result can invite a sort of skepticism on mathematical explanation. Why? Because a question arises spontaneously. Is explanation 1 all there is to mathematical explanation? So Ellen says a why question or explanation 2 is not all there is to mathematics, but then is explanation 1 all there is? Maybe there's nothing more. And in fact, some people have expressed precisely this skepticism. Zelker has said, I argue here that given the way philosophers have been using explanation, the term is not applicable to mathematics as it is in science. So there are some people that just say it's a dead end, like you're just looking for a chimera or something. Maybe that's right, I don't know. But if Inglis and Meyer Ramos and Lett are right, then the result may be taken to show that in fact there is no explanation to at all. Maybe that Zelker is right. Maybe that's an important result, but I just would like to see this connection more explicitly. And here I wanted to say that even if we want to or try to get a more objective account of explanation 2, it doesn't mean that we have to be totally insensitive to the context or to the audience in which mathematics is done. And in particular, Mark Brown says, talking about explanatory proof, whether a proof is explanatory may also depend on which feature of the theorem are salient to us, like made with a specific cognitive architecture, etc. But despite this context-sensitive feature, it does not follow that a proof is explanatory merely by virtue of striking its audience as explanatory or by generating understanding on the audience. So there is a limit to the context sensitivity, whereas other people want to go really further down to the context sensitivity to say, look, explanatory is just in the eyes of the beholder, it's just what strikes the audience as explanatory. And that seems cannot play a role in scientific explanation. So let me end here with a last discussion of a very interesting recent paper by some people who are here and others who are unfortunately not here. I was hoping Pablo would be here, called Mathematician Assessment of the Explanatory Value of Proofs. So here we have a proposition, and the idea is like to compare 9 proofs of this proposition taken from a recent nice book, Ording's 99 Variation on a Proof book, and ask mathematician, is this more explanatory than the other? Like a comparative judgment analysis. I think the methodology is really promising, and it's used for the first time in this context. So that's really cool. But I have some qualms about the way it's implemented and the discussion of the result. So first of all, they say, actually this is a quotation, the full set of explanation, typeset as seen by participant is given in the appendix. So explanation, full set of explanation. So that's weird. So I would say the full set of proofs, but in fact they call them explanations explicitly. So already they are giving the assumption that those things are explanation, already implicitly denying Mark Lang's approach or many other philosophers' approach. We're gonna say this thing doesn't admit any mathematical explanation whatsoever because it's an obvious like routine calculations to find the results. It's not the kind of thing that we should ask an explanation for. The result is still very interesting. They found a very high level of agreement among research mathematicians. And they actually tried to be very explicit in their prompt to look for explanation 2 and not explanation 1. In fact, they explicitly said, in each paired comparison, we want you to think about which argument best explain why the proposition holds and not to focus on how it might be received by a particular audience. So they tried to explicitly look for what I called, I think, explanation 2. Yeah, so to focus on the explanatory value of proof. Okay. So here, just to give you an example of the 2 of the 9 proofs that were compared, This is the elementary proof. So we have, this is a very simple result. It's a degree 3 equation, and we just do some manipulation, algebraic manipulation. We expand the linear term 9x. So we just like expand the thing and find the zeros. And then we have the 2-column proofs. This is something I never saw before, but I think it's popular in the US, that people are taught in school to like write things in 2 columns and write y is one thing the same. So it's basically like the same proof, or they think is the same proof in a way. I will show the quote. So they say, despite the 2 proofs presenting what we see as being the same underlying mathematical argument, so they think these proofs gives the same argument. However, mathematicians gave like very different accounts of, they evaluated these 2 arguments differently in terms of their explanatory power. Our participants perceive them to have very different explanatory powers. This is weird because it seems like explanation is attached to proof or argument. And so if it's the same argument, it should have the same explanatory power, especially if you're looking at explanation 2. And in fact, they are very explicit that the mathematician, notwithstanding what they were told, did not look at explanation 2. They write, even when guiding mathematicians to interpret the explanatory value of a proof, in a way like in explanation 2, they seem to have considered factors other than the mathematical reason offered by the proof for why the proposition holds. Those factors could be related to how easy it is to understand them. And in fact, this to me is very consistent with the previous results by Inglis and Aberdeen from 2015, in which they linked explanatory proof to useful, precise, and non-intricate proof. That's what I think they were tracking. And in fact, like I talked a lot with Pablo about this, and we have in program to do a new version of this experiment, precisely similar, but just not use the word explanatory. And I predict we're going to have the same result. And if that's true, then it shows that explanation is not really what's at stake here. Okay, so here it was just a quote by Mark Lang in which he says that simple results like the one analyzed here are not the kind of thing that call for an explanation. I already said that. So I see like a couple of problems in this setup. Problem 1, why call the proofs explanation instead of proofs? That already assume a specific view of explanation to the mathematician. Problem 2, asking mathematician to choose one or the other forces them to make a judgment of explanatory value, even in a situation in which that might be not appropriate at all. Like they are forced, it's like yes or no question. They have to choose one or the other. And maybe they're just tracking what is better, not what is more explanatory, because they are obliged in some sense. Conjecture, what I just said, we would be able to obtain a similar result if we run the test without using the word explanation. That's an empirical conjecture. I don't know, like we should test it, but I think it's interesting. I would like to know the answer actually. Okay, concluding very quickly, of course, out of time, just a little argument here. Contra Zelker, I am also an optimist, and I think there is such thing about explanation 2. That's my first premise. Second premise, explanation 1 and explanation 2 are different phenomena. Third premise, if explanation 2 is just something that generates understanding, then explanation 2 gets reduced to explanation 1. Conclusion is it's not the case that explanation 2 can be characterized in terms of the understanding it generates. That's what explanation cannot be. And when I say explanation, obviously I mean explanation 2. So one could argue against premise 1, and of course, but then I would like to see this made more explicitly. Maybe the skeptic is right, and there's nothing really under the heading of mathematical explanation besides explanation 1. We don't know. I didn't talk about positive proposal like counterfactual accounts also applied to the case of mathematics, or mark account, etc. In any case, what I want to emphasize a lot is that the study of mathematical understanding is really important. So I'm not saying explanation 1 doesn't matter. I just say it's not explanation, but I think it's one of the main things we should study, especially if we do philosophy of mathematical practice. So conclusion, I showed that there are 2 distinct phenomena that are called mathematical explanation, a technical and a pre-theoretical one. Explanation 2 is a type of scientific explanation. Explanation 1 is a broader phenomenon. to avoid skepticism, we should be careful not to conflate explanation 1 into explanation 2 into explanation 1. And this, I think, is an example of why doing interdisciplinary research is so hard, because like some people in the math education community don't care at all what philosopher thinks, and some people in the philosophy community don't care at all what the math education thinks. But there is a subset of both communities that care, but it's like harder if they have to share the terminology with their respective community who don't care. So that's why like we should step back and do some work, some preliminary work, I think, together to make sense of these things. So it forces also more generally to think hard about the type of empirical evidence that can be relevant for philosophical discussion. So thank you.
Questions? Thank you, Silver. Wonderful paper. So I have a thought and maybe an objection. Let's see what it says. So commenting on that Ignis and Aberdeen result that was cited there. So that was the starting point, or just as a comment, that was the starting point for an abortive project that didn't lead anywhere because of my laziness and Matthew's skepticism. But I noticed that those three criteria that we come up with were very similar to the criteria that Carnac proposes for explication. So, which I'm not going to attempt to remember off the top of my head, but they're very similar. So this just came out of nowhere, so I thought that was intriguing. That was worth pursuing, and we didn't pursue it. But the follow-up I would have made with that is that I would have suggested that Carnac's account of explication, at least as far as mathematics is concerned, is actually a viable answer to the question of what is a proper understanding of mathematical explanation.
Okay, interesting.
Perhaps because mathematics is more of a formal discipline than empirical discipline.
Yeah.
But I understood this as being a contribution to what you're calling explanation 2, but you're saying that Matthew and I were actually a clear-cut example of explanation 1. So that leads to my objection/question, which is, are these things really distinct, or have I really misunderstood this?
Yeah, so the question for the audience online was something along the line, the 2015 project identified some criteria for explanation that actually are criteria to better understand Carnap's notion of explication rather than explanation. But then a conjecture was maybe in the case of mathematics, these two things go together. So I didn't think about that. That's interesting. I don't know, certainly that's not true in science. And that goes in line with my verdict that those criteria aligns better to explanation 1, because I want to say, so explanation 2, the basic idea is really to have a continuity with philosophy of science. It's like to take that thing they're doing, the philosopher of science, and say, is there such a thing, obviously like appropriately changed for the case of mathematics or not? The skeptic is gonna say no. Maybe you are also gonna say no, and so say that it just conflates to this more broad discussion on understanding, because I don't remember now the criteria, but there's something like non-intricacy, simplicity, things like that, things that are clear indications of understanding. And for me, like the most clear-cut thing, like the way I really started to think about it, I think also talking a lot with Marcus Giaquinto on this, is that there is a big difference between understanding why a conclusion is true and understanding how an argument supports the conclusion. And those criteria seems to be relevant for the second question, how the argument supports it. Is it a perspicuous argument I can have a clear grasp? Is it convincing, etc.? So that's, to me, explanation 1, and your conjecture would just lead to a form of, I would say, skepticism with respect to genuine mathematical explanation. which might be like warranted.
Yeah, I mean, one of the reasons why the scientific approach, at least, I mean, there are multiple competitors as to what's the right approach to the scientific explanation, but some of them are clear non-starters as far as mathematics is concerned. So
yeah, causal.
Causal, exactly. So, so if you end up going down that path, then you kind of answer the question before you pose it. You say, well, the best kind of scientific explanation is causal. Mathematics look at causation, so internally, so.
No, I agree. So you don't want to go too far down that path. And I think like a good middle way is the work of Mark Lang, who's certainly influenced by the philosophy of science, but is also emphasizing the presence of non-causal explanation in science and in mathematics. Yeah. So obviously there are going to be differences. But I mean, I'm not very familiar with the literature, but there are also people who are trying to use the notion of grounding, so metaphysical explanation in the case of mathematics, or even like counterfactual analysis within possible worlds. Maybe these analyses are not, I don't know, will work, will not work, I'm not sure, but there are ways to do that in a way that continues with the philosophy of science. And there's certainly the aim is to go for explanation too. Certainly grounding is in that direction. Some people say that explanation and grounding in mathematics go
Explication gets linked to grounding, so then that's where we began. Anyway, much more.
Thank you.
Hi, Sylvia. I thought that was great. And I think, well, I like the distinction that you put about I was wondering about Matthew's results, Matthew and Connie's results. If you say that they're about explanation one, wouldn't they, and suppose your hypothesis probably turns out to be true too, wouldn't that be saying something about mathematical practice, that when mathematicians talk about explanation, they mean explanation one? And if that's so, wouldn't explanation two, that still could exist, and it's still a very valid philosophical pursuit, but would that not question whether explanation two isn't really about mathematical practice? Because yes, mathematicians in print say they want explanation. Yes, but they talk about explanation, they're talking about explanation one. Wouldn't the PMP, isn't that evidence that they should favor explanation one, not explanation two?
Yeah, so the question was, what are mathematicians talking about when they talk about explanation? Since the empirical results I presented here suggest that mathematicians refer to explanation one when they talk about explanation, and what philosophy of mathematical practice should think about that. I totally agree. I think that explanation, scientific explanation, is a technical philosophical term. Mathematicians are not philosophers. Mathematicians use the word explanation as my dictionary uses the term explanation, which is exactly explanation one. Ask dictionary.com or ChatGPT, what is mathematical explanation, or what is explanation? It means understanding, make plain, and like this kind of thing. So I totally agree. That's why there is some suspicion also in using all these empirical techniques of like counting the words explanation to go at the phenomenon of mathematical explanation, because yeah, I just think you are absolutely right that they do not point at explanation two. Is that a problem for mathematical practice? Maybe. In fact, a lot of accounts, I think like mathematical explanation, the topic has gained traction in analytic philosophy precisely because it's a little bit detached from the praxis, precisely because we can go in the metaphysical direction and just like do these very abstract things. But I think there are also middle ways. And again, I'm going to refer to Mark Lang account here because it's the one I'm more familiar with. And I think like he has, his account is an example in which he takes the practice very seriously, but nevertheless he's very strict about his idea of giving an account of explanation too. But taking the practice seriously doesn't mean to take seriously what mathematicians say. It means to take seriously what they do. Like the product of the practice. Who cares? Like if they use the word in one way or another.
So now you have speaking out explanation too, if we can't trust the words.
So that is also the separate question. It might not the value of explanation 2 might not be like pragmatic in the same way as explanation 1. That might not be like, who cares if they seek it or not seek it? Like, we are just, in some sense, like from the kind of more technical philosophy of science perspective, some accounts certainly are pragmatic and have pragmatic elements. But even if they do, I think that would be a secondary concern in some sense. Like, the primary concern is really like to try to find the structure, how this phenomenon works. And I think, again, I think there could be ways to design experiments to track explanation 2 by interacting with mathematicians, but it has to be very careful, and we should be super careful not to introduce some assumptions in the prompts in the way I suggested was done.
So we try to go short question, short answer. If you want to take Henry.
Yeah, lovely talk, thanks. I was wondering whether what's really going on is that in maths education, there's an emphasis on being able to operationalize what you're doing. And you kind of were talking about this with the experiment about markers, but it's not really like two different phenomena. It's just that as a philosopher, you can say whatever you like, really, but when you're doing an experiment, you need to be able to measure the outcome of what you've done. And such that the explanation one, as you're calling it, is really just tracking like the favorite measure of like something you can operationalize in various ways that we're doing. And like, I feel like the danger with like Marcus's kind of response, like, oh, that was just about proof presentations. It's just that you end up in this kind of no true Scotsman thing. And if you say, okay, I'm interested in like characteristic property, and then Matthew does an experiment saying, well, actually that didn't work. Your philosophy is wrong. You say, no, hold on, that's not what I meant. I meant this other thing that's more woolly that isn't endowed in that way.
Yeah, thank you.
Kind of failure in operationalization.
Yeah, so the question was about operationalization. I don't know. But anyway, like the idea that in the math education, we have to test things. We can't just do, as philosophers do, just like invent whatever. But so we need to operationalize these notions. So that's why maybe we want to get that more explanation 1. So I think that's not true because, for instance, like Tania Lombroso, she's a psychologist and she has to test a thing even like massively. She does that all the time. She has a lab and a lot of experiment with children. But she's very sensitive to this distinction, or like part of the distinction. She's kind of in the middle. But she wants to be very explicit that her notion of explanation is an answer to a why question, and not, as some people in the math education community say, also a how question. And she thinks that actually focusing on why question really highlights some specific feature of something along the line of scientific explanations and have some precise result in how children think. That can be quantified. So I think it's very interesting. So I don't think we have to renounce to empirical studies at all. I just think that more care should be put into it. And so I think like if we reason hard about this stuff and talk and be like with ourselves also, like a bit more clear, what do we mean when we talk about proofs? What do we mean when we talk about explanation? Then maybe there is a way also of doing these experiments that is more sensitive to these philosophical distinctions. Again, like I think I would totally, I'm curious about this, and I would, with Pablo or other people, I would like to design a new experiment to test whether this is correct or not. It's just an empirical also question.
Yeah, so thanks very much, Silver. That's great. I've got 3 comments. I really think, to my ears, you're like essentializing disciplines in a really strange way. So, for example, Marcus's complaint about our study, I don't think that's because he's a philosopher and I'm not. I mean, that's, if you go to a psychology conference, all of the discussion is about how to interpret experimental data. That's just a typical way of thinking about, can you interpret these data in that way? That's just a totally normal, you know, I think you're attributing things to disciplinary differences that are not fair, not due to disciplinary differences. That's my first comment. And I think you do that in the second bit as well. So, for example, the function of account is not because I'm allegedly a maths educator. You know, that came from Daniel Wilkenfeld. He's a philosopher. You know, it's a philosophical account of explanation. I
know that.
You know, I mean, so in what sense you can't attribute that to disciplinary differences?
Should I answer first? Maybe
As long
quick.
as Yassine lets me come back to answer that.
Yeah,
Okay,
I
let's do
answer
that.
very quick. Short. Okay, I'm essentializing the disciplines. So I'm just giving you a general impression. So in the conference I was at Rutgers, there were some math educators like Pablo who are in interaction with philosophers, some were not. The one who were not were very, very clear that they didn't care about the explanation of philosophers of science. The one who were, no. But you see, like I think like this, there are some disciplinary differences in the way we use this term normally, because math educators are generally more interested in understanding and yeah, so it's kind of natural to think of explanation in those terms. But I don't want to say it's essential or like, you know, like doesn't.
And then the second point is about so you asked about the relationship between Zelka and, I'm really sympathetic to the Mark Zelka account.
Okay, perfect,
Totally
yeah.
persuaded. But the reason I wouldn't want to phrase it in those words, and maybe this is a disciplinary difference there, I know, I contradict my earlier claim, is, the way I would talk about your explanation too is I do not require that assumption to explain all the behavior. Right? So I think I can account for all the behavior I observe without requiring the assumption that explanation to exist. And I think if you disagree with that, you need to find me some behavior I can't account for. So I'm suspicious it exists, but maybe it does, I don't know. But if you could provide me with something I can't account for.
I see. Yeah, that's similar to Fenner question. To operationalize things. Yeah, because like philosophers say, look, there is this distinction, but in fact, it doesn't explain any difference in behavior. So like maybe people would be.
Well, you can always invent distinctions, but distinctions, not just keep inventing distinctions for no purpose, right? Distinctions need to be there to achieve something.
No, exactly. So, but it could be a philosophically idle.
Yeah.
No, I think there is a margin for work. In fact, this is just kind of initial thoughts, and I'm glad, in fact, to discuss more.
And then my third comment is to you and I and Benham indeed I think we have the data you requested in your change the prompt. So I think we have that data and we can look at it.
Oh yeah?
Yeah.
Okay, let's do it. Okay, great.
Okay, so let's thank again. And there was a long.
Oh, okay.
So Joachim has a comment, but you can read.
And no questions. Okay.
So there's no question. Okay, thank you very much. So we reconvened at 4:15 with an online talk by Natalie. So Natalie couldn't be here. So she's gonna talk about. Yeah. Like we have to settle things up. So set things up. Hey. you see us?
Hello. Yes, I can
Hello.
see.
Oh, good. So you managed to get in. Nice. So now we have to see how to share your screen.
Okay.
She should be able to. Do you have something called present at the bottom?
Okay. Slides.
You have to click on the present button.
I have to do what?
To click on the present button. There is a stop screen and present.
And then slides or share screen?
Yeah, slides or screen, whatever you wish.
Slide or screen, as you prefer. If you click on slide, you will upload the presentation on the stream, which is nice.
You prefer that?
Is it PowerPoint you have or
yeah.
PDF?
PowerPoint.
Can I say hi to Natalie? So it's a wife, it's Valeria from We Met in Nancy. I'm sorry that you didn't you couldn't come, but I wanted you to know that I'm in the audience and looking forward to your talk.
Okay, I'm gonna share my screen.
Yeah.
Okay, that works as well.
Yeah, no problem.
Spewing back. Wisdom that I've learned from you.
Do you see my screen?
Not yet, no. But wait.
Oh wait.
We have to wait. It's going to appear on our screen.
Allows people to see your screen. Oh. Select window.
Do you see your screen on your computer?
Yeah, it's not letting me select the PowerPoint.
Okay, can you try the slide option if possible?
Oh, I got it.
Oh, you got it. Okay. Oh, yeah, perfect.
Oh, nice. We see it.
got it.
That's perfect.
Okay.
Can you try to use the slideshow? Yeah.
Is it good for your side?
Let's try the slideshow. Let's click on the button that you're on.
I clicked the slideshow, but it could be that my slideshow is not in full. What do you see? Oh yeah, you see my. Oh no, I see what you see. Okay.
I see your note. Do you need your note? You need your note for the talk?
No, I don't. How should I get out of? Okay, just a second.
I think there's a small. Oh, your mouse was on the on the bottom. What's the?
Yeah, I was here, right?
Yeah. So yeah, if you click on that.
Click there. Yeah.
But I see my full screen, but I can see that you don't see it. Let me.
Do you have two screens or one screen?
I do have two screens. Maybe I should get my other screen.
So can you swap the screens around?
There's an option of sweeping the screen. Forget where it is, but it's on the top,
yeah,
right?
so if you're using PowerPoint, the one with the notes, there should be towards the top something called presenter options. But you're on a Mac, so I'm not
I think
sure.
it's above.
No, she's on a Mac, so it'll be slightly different.
Maybe on the other screen. Can you go with your mouse on the other screen?
Let me just see.
No, yeah, it might be on the other screen. So
can you get your
on the second screen you have? Is there something called presenter options towards the top?
How's that?
Oh, this is good.
Perfect.
Now this is working.
Yeah.
Is it working for you as well?
Yes, it is.
Okay, cool.
I can't see you, but I can see my PowerPoint.
Yeah, I don't think there's a way to see us. But I think it's okay.
When you end the PowerPoint, hopefully you should be able to see us.
What do we do for the questions? Do we?
Well, I'll stop my PowerPoint.
Yeah, and then we'll be on video only.
But then you're gonna just you're not gonna see the audience. You're gonna see us.
Yeah.
Oh, is this
I
on
can
good
turn
for
the,
the
I mean, I can turn the camera on.
Oh,
but I don't know if everyone wants to be on camera. Was
Yeah,
presented
yeah, you're right,
earlier,
right.
you need a presenter.
Yeah. No, let's. We're not gonna show the audience because maybe because this is the live stream, we have to ask for authorizations. I don't know.
Yeah.
So, yeah. For the questions, maybe either we ask people to come here,
Okay.
or I'll come and
Or we can take this.
or we can
around
take
if you
that
want,
around.
yeah.
That's pretty cool. Yeah.
Just switch it on and then just take it around.
So I should turn it on. Or?
Yeah, we can turn it on now.
Is the sound loud enough?
Yeah, I think so. Natalie, do you just want to say something again? See if we're loud enough here in the room?
Yes, hello.
Can you hear me? Yeah, we can hear you. Perfect. Thank you.
It should be, you have to put it a little bit louder.
Yeah.
So now we have used.
Okay. That should be
You can talk to Natalie.
Oh, I'm back. How, Natalie? Hi again. How are you?
I can't see you. I'm going to stop sharing the screen so I can see you.
No, don't worry. Don't worry. How are you? Yasin told me that you're very busy. Your chair or something now?
Yeah, Dean.
Dean, okay.
It's terrible.
No, I'm sure you're. No, but I hope there will be other occasions. Because with COVID and everything, I don't know, I have this feeling that time was too fast, and I'm sorry that we didn't have other occasions to interact. Or
I know, me too. Me too. But I'm reading a chapter you just sent in to Bharat.
Yeah. Oh, how? Oh, okay. Good. No, please read it because I was so late that I have 2 days to make changes. So if you have any suggestions, I don't know. It took me so long to write it because I didn't want to write the same article I've already written like too many times. And so I tried to give, as you see, this kind of narrative to. But if you have some references that I think should be good to put in,
Okay.
I will let me know. Bye. Have a nice talk. I'll see you later.
Well, I'm supposed to talk for 20 or 25 minutes?
I think it was.
Oh, sorry.
No, don't worry. It's 30 minutes.
Okay.
Can you hear me now?
Yeah.
So Yasin told me 30 minutes, and then it's 50 questions.
Okay,
That's,
sounds good.
what it is. See you.
Yeah. We just they're just getting some tea and coffee, so there'll be a couple of minutes. So
okay, I'll go get some water.
No problem. Can you see us still?
Yes.
You can see us now?
Yes, I can.
Yeah, perfect. Okay. So when you finish your presentation, we'll switch it from here so that you can see whoever's coming up to the front.
Okay, sounds good.
If you do want to, no one will be at the front, but if you do want to see who's at the front, you can open this YouTube stream in a separate window. Just mute it, but you should be able to see the stream, what we're watching now, in a separate window.
Sounds good.
Yeah. But yeah, grab some refreshments. We'll be back in 1 or 2 minutes. Thanks.
Is it going to work? Yeah. There's some feedback on that. That's unacceptable.
Okay, I'm going to close the door. No, okay. Do you still have a phone in your office?
I think she should.
I'll let you know when we're going to start. The people are still. We finish a bit late, so.
Do you want?
No problem. Hi, Gila.
What?
You can talk. You can talk now if you
You
want.
can talk if you want. Okay.
She's gone. Well, let's come.
Okay, I'll go and say something.
Yeah. Okay.
Yeah, you. Or you would tweet.
I try to.
Oh, that's nice. Yes.
Yeah.
But yeah.
But nobody in that room.
Actually,
So that was.
Yeah, no, he said he has the data.
Yeah, that's true. But that's true in this regard. Yeah. Yeah.
Interesting. Well, I want to have a proper conversation about that.
yeah.
Well, I'm going to have Well, I know.
Yeah.
Just because usually like as a theory.
Yeah.
Theories that explain
Yeah.
So are we good? What's the situation?
Oh, I can feel what you're feeling.
Yeah.
So then we can add.
No.
Ah, but we don't. There's still the. We don't have it. Oh, she's gonna do it. Ah, perfect. Perfect. Okay, I think we are ready to start. So this is the last talk of today. So we're welcoming Nathalie Sinclair, who is in Vancouver at the moment. So it should be early. And so she's going to talk about aesthetics and mathematics applications. So the floor is yours, Nathalie. Thank you.
Okay, thank you very much for inviting me, and thank you to the organizers and also the everybody who's there for allowing me to come in on Zoom. I'm really sorry to not have been part of the conversation. I know it feels a bit strange to have me just parachute in here, and I hope that there's some opportunities for me to hear more what was said before my presentation and after mine, in order to be able to learn from you and contribute, I hope, to your discussions. So my talk is a little bit hard to parse, perhaps. I do think that there's some interesting overlaps with the theme of the conference on math education and philosophy of mathematical practice. I think my work sort of straddles definitely math education and philosophy. And so that's where I'll be talking mostly, and then looking forward to questions and comments on the relation with philosophy of mathematical practice. So the three elements to my talk, the first is around aesthetics, mathematical aesthetics. So I think that's something that many of you are familiar with, even though there's not a ton written about it. It's definitely an area that has interested several people, including some people in the audience. But I also want to talk about aesthetic and math education. So thinking about how bringing these ideas from aesthetics and mathematics into concerns with math education. And the third one is about math education research. So how do issues of aesthetics come to play in mathematics education research? And this is a picture of one of Robert Boyle's early experiments. And Robert Boyle is often taken to be sort of one of the central players in thinking about thinking about the scientific method and how it is you convince people that something has happened even though they weren't there. So this image was one of his important ways of convincing people that his machine actually did exist and that it did the things that he claimed it did in his written words. So I'm going to come back to this early idea of method and try to rethink it in the light of aesthetics. So those are the three parts of the talk. So I want to begin a little bit because there's so many different ways of thinking about aesthetics and those ways have changed over time, including in my own thinking. So I thought it would be useful to map out some of these differences. I think most people sort of think about aesthetics in the way that Baumgarten and Kant had us thinking about it in the 18th century. Which is thinking of aesthetics more or less as the art of good taste that involves some kind of disinterested contemplation and that assumed a sort of universal understanding of beauty. So that gives aesthetics its place and its alliance really with art and with museum art and determining what is beautiful art and how you come to develop a sense of what is beautiful art as an art critic, let's say, or a member of the public. And that's quite related to sort of the colloquial sense of aesthetics, which is what is made pretty or beautiful, and sometimes even a style or a look. If you look at the fashion industry, they talk about the aesthetic as a style or a look. And so from these ideas of aesthetics, we certainly get a sense that the aesthetics is really about some kind of high art and some kind of elitist endeavor. And that has certainly been a theme in a lot of the research on the mathematical aesthetic. But before Baumgarten and Kant, the aesthetics as an etymological way of understanding it from the ancient Greeks was of or for perception, senses, to perceive the senses, or by the mind to feel. So aesthetics in that sense is a way of knowing through the senses. Which is quite different from the view of aesthetics that I just mentioned below. And so one question is, how does the word aesthetics sort of shift from this kind of knowing with the senses to kind of value critique kind of idea from Baumgarten and Kant? And I'll talk about that in a little bit. But from these different ideas of aesthetics, some tensions have emerged in the literature about whether aesthetics is some kind of rarefied ability, especially in mathematics, or whether everybody has an aesthetic sense and potential for aesthetic experience, which was Dewey's point of view. Is aesthetics objective? Does it belong to the mathematical idea or proof itself, or is it subjective? Does it depend on the mathematician, on the culture, on the context? Is it mental in the sense of the disinterested contemplation of Kant, or is there something sensual about it? And finally, is it something that's sociocultural, which the work of Adorno was really trying to push? Or is there something more sensory and nature-based about it, which is what some of the recent research in neuroscience is showing? So these tensions really matter in terms of how we're going to study aesthetics in mathematics or mathematics education. And the definitions that we use about aesthetics really matter there. So In my own work, I shifted, in my early work, I shifted the question that was usually asked in the literature, which was what makes an elegant proof or an elegant or beautiful equation or so on, to a more pragmatic kind of question, which was how does the aesthetic function in mathematics? So I was less interested in what counts as a beautiful proof than in how do evaluations or sensibilities to beauty affect what it is mathematicians do. And I've said this was a more pragmatic approach because it was really coming through the work of Dewey, who was a pragmatist and as a philosopher. But I'm interested in how this aligns maybe with some of the work in the practice of philosophy of mathematical practice. Anyway, in my own work, I found that the aesthetic has three functions: the motivational, generative, and evaluative. And so it guides mathematicians into choosing certain problems to work on and how they want to work on it, in actually solving those problems, finding sort of strategies or insights into those problems. And then finally in evaluating or determining which are the proofs are worth writing papers about, which proofs are worth publishing, and that kind of thing. So those different are really things that I identified through looking at the literature in mathematics, but also by interviewing mathematicians, practicing mathematicians. And I was interested in that question, not really because my focus was on mathematics or mathematical practice, but I was interested in the questions as they might pertain to mathematics education. Obviously, aesthetic is just some kind of remedy for gifted kids, let's say. Then that changes how you might want to take it up in math education. I was following the ideas of Dewey and of Papert, who argued that the aesthetic isn't a rarefied thing, that you don't sort of turn on your aesthetic responses when you walk into the mathematics classroom, and that there would be ways to engage all learners in aesthetic experiences. So that's why I wanted to look at these three different functions, because they provided alternate ways for thinking about how the aesthetic might be relevant in math education, not just do they agree on what is the beautiful theorem, but do they mobilize aesthetic responses when they do mathematics. So in my early work, I created a color calculator, which was basically a way of being able to see and think about fractions like this one, which is 1/7, in a more visual way. So each number gets assigned a color, and we can lay them out in a table like this. And when I did work with grade 7 students, I found that when it was those fractions were laid out in these colorful tables, they had lots of interesting problems that they posed, like how can I get the table to be all red, or how can I get that diagonal to be columns, or many other kinds of questions like that they wouldn't have asked if they were just looking at the numerical representation shown above. So that was really looking at mathematical problem posing and the role that aesthetics might play in problem posing. And as you can see, it was very closely linked to a notion of aesthetics that relates to perception and senses, because it's about how do I sense mathematical ideas. And in this case, the visual sense was very important. I later developed, working with my colleague Lulu Healy, who was working with blind students, also a auditory experience of fractions, which I play for you. I warn you that it's not the most beautiful sound you'll ever hear, but just to give you a sense of what I mean. So that was another way to experience the fraction 1/7. And just as an aside, when we worked with the blind kids with this sound calculator, there were several of them who actually cried when they heard that. It was such a moving experience for them to have this other way of just imagining or feeling what it is that 1/7 might be. So I just wanted to give you this example to show you sort of how I was thinking about the aesthetics for a while. And I'm not the only one, oops, sorry, who has worked in this area. Recently in 2022, there was an article written in the Journal for Research in Mathematics Education that took up this idea, these three different functions of aesthetics in the context of math fair. We're looking at how young children engaged in different aspects of the math fair. So you can see that they looked both at the generative, the motivational, and the evaluative in terms of what it was that the students were doing as they were working at the math fair. So now there was another shift in my own thinking about aesthetics that was prompted about 10, 12 years ago when I was working with Elizabeth de Freitas on the book Mathematics in the Body. And here, again, instead of looking at what is mathematical elegance or beauty, or even how does it function, I became interested in the question is how does the aesthetic operate in the creation of norms and sense making? So if we think about the aesthetic as a way of understanding through the senses, and also a way of deciding what's beautiful, then we should wonder, like, well, who is it that gets to decide what's beautiful? And how does that matter sort of in mathematics itself and also in math education? So this line of work was heavily influenced by Rancière, who's a philosopher who became interested in the notion of the aesthetics as being political. And he took up this sort of dual way of thinking about aesthetics in the literature, which was, briefly speaking, you know, are we talking about the art of the beautiful or the art of the living, which we can think of as a sort of mode of judgment or an experience. And he wanted to see how those two concepts sort of aligned. And one way to express that is to look at this mix of what can be sensed and what is then taken to make sense at sort of a common sense level. So what can be sensed, literally, what is available to the senses, made available to the senses, illicitly, implicitly. And then which of those things that are made available to the senses actually count as being sensible. So Rancière, who was working specifically in the domain of arts, found that the political aesthetic operates through this paradoxical mix of autonomy and dependence. So the dependence comes from, let's say, the painter who's engaged in actually painting with the paintbrush and the oils and the canvas, where there's a strong sense of dependence of the artist on what the painting looks like, what it feels like, and so on. And then when that painting goes into the art museum or the art gallery, it sort of has a life of its own. So it has this autonomous sort of existence that's almost independent of that sensory experience that the artist had. So in work with Elizabeth de Freitas, we looked at Rancière's argument, and we argued analogously for mathematics, that the aesthetic functions politically also in mathematics, also through this mix of autonomy and dependence in determining regimes of sense making. And I'll just provide a few examples. In our book, we have a chapter where we look at several examples, mainly in the history of mathematics. But we can think of how different modes of sensing are operative in proving over time, particularly, I guess, if the example that we elaborate on is based on Reviel Netz's work on what proof looked like in the time of Archimedes, and how that changes over time, how that's related to both what can be sensed and then what actually makes sense as a form of proof in the community. Then there's concepts like infinitesimals also that operate with different forms of sensing. Can you actually see infinitesimals? And then how they are taken to be the sensible way of thinking in calculus or not. And I'm sure you know the history of how that has played out. So that history isn't just about mathematical truth or correctness, but it's a history that's aesthetic and political because it determines what can make sense. And then in tools, or in the means of doing mathematics, I think the computer-based proof is a really nice example of how this political aesthetic functions. So that's one way of thinking about, another way of thinking about the aesthetic in relation to mathematics. And again, the goal of looking at mathematics is also not just to look at mathematics, but to think about mathematics education as well, and how these ideas might play out in our work as math educators. So I want to give you an example of a video, and I hope you, can anybody tell me whether they heard the 1/7? Can you hear me? Just checking if you can hear me. Hello?
Yeah, can you hear me now?
Yes.
Can you hear me? Sorry, I wasn't. Yeah, no, we could hear you well for the sounds. And
okay,
so
super.
Okay. Go ahead.
Okay, thank you. Okay, so this is a video that comes from a elementary school Head Start situation in Ontario. So these are grade 4 kids, and they're using a multi-touch iPad application that was developed in 2014. And in this multi-touch iPad application, you'll see that the kids are engaged in what we've called a gestural arithmetic. So they are expressing mathematical ideas through their gestures. So as you can see, this is a different way of offering students a sensing of mathematics. So we're aestheticizing mathematics by offering them a different sensory experience with it. I want to you to pay attention to what the little girl is doing with her hands, and to consider what she's doing in the backdrop of the fact that in math education, many researchers and teachers actually have told students that they shouldn't use their fingers or their hands when they're doing mathematics, because that's not the proper way of doing mathematics, because it's not sufficiently abstract. So I'm setting this up because I think it relates specifically to this question of the political, because it's about what we allow the senses to do in mathematics education. So here goes the video.
What do you think will happen if you put the 2 and the 2 together? Can you tell me what you think might happen?
It will turn into 20.
20? Okay, let's see what happens.
4.
4. 2 and 2 together. 2 and 2. Yeah, it makes that. 4. Can you make another 4?
1.
So you made a 1 and a 1, and you put it together, and you got 2.
2.
2 and a 2.
4.
Oh, that's how you did it. You put 2 and 2 together?
Yeah.
Really? Oh, can I try?
Sure.
Okay. 2 and 2. And then what do I do?
You just put them together, then it makes 4.
Really?
So what's important for me there is the way that the gesture that the young girl has used on the screen now becomes a gesture that she uses to communicate with me and also with herself. So the gesture is operating as a way of sensing addition in this case, that she actually simulates when she's asked to think about what will happen, what she thinks will happen. And it's that simulation that helps her come up with the sum, actually, of 4. So it's a very different kind of sensing of addition that some people might decide is sensible and some people not. So obviously, in my own work, which is based on theories of embodied cognition, this is a sensible way of thinking about addition. So how do different ways of sensing make sense in other socio-material environments? So this is a question that I think is very interesting in the work in math education that's looking at culturally appropriate mathematics and that's thinking about decolonization of mathematics, is to think about how it is the aesthetic is operative in determining what mathematics means in different cultures. So this is an example of an elder from a nation in Alaska who's talking about his way of thinking about what we would call the Cartesian coordinate systems, but for him always starts at the center where he is. So it's a very sort of polar idea of a coordinate system, which is a way of making sense of his environment, locating himself in space, that's quite different from the sort of external Cartesian coordinate system that we think of as being unrelated to any particular body. So here you can see a different sense of aesthetics that operates on basically a very similar idea of how do we talk about locating oneself in space. Another example, which is much more, let's say, small scale, is how some cultures, for example, Koreans, see that fraction, which in English we say is 3/4, but for Koreans is 4 things divided into 3 parts. So again, a very different way of sensing a fraction, in this way expressed through language, that changes what it is that makes sense in mathematics. This is an example that comes from Canada and the Mi'kmaq peoples of the East, and how important for them verbification is, as Lisa Lenny Borden calls it, in their way of understanding mathematical ideas. So objects are not static, but they actually are always in verb form. So a line isn't straight, it goes straight. So again, this is a different way of sensing mathematical concepts. And I think that the words of the mathematician Bill Barton are really interesting for us here, is, as he says, a proper understanding of the link between language and mathematics may be the key to finally throwing off the shadow of imperialism and colonization. And I would argue that this isn't just about language, but it centrally involves the way we sense and make sense of mathematical ideas. Okay, I'm going to close with the third section, which is on math education research, and drawing on the ideas of investigative aesthetics from forensic architects who have been working in London and now across the world, who basically come to crime scenes, and instead of just interviewing people and collecting data from the crime scene, they reenact the scene, so that they are able to aestheticize that scene and understand what it would have felt like to be at that scene, how loud the gunshot really was, whether anybody could actually see around the corner, things that are simulating of subjective experiences. And they do this because it allows them to get at ideas, at forms of experiences that you can't in typical investigations. So in mathematics education, we have used this scientific method that comes out of the work of Boyle's, in that we seek objective descriptions of what happened in the past by a reliable witness. And to do that, we use transcripts and language. But the problem with transcripts and language is that they rely heavily on discourse and objectivity. And so we do not get to these sensory experiences, which are so central to the aesthetic. So if we want to aestheticize research, how might we, for example, think about doing reenactments like the forensic architects do, where we can actually sense what was done and not just read about it or even just see it, and then move away maybe for relying on words and visuals. So I'll give you an example of a reenactment idea that draws on the work of Wittgenstein et al. This is a young girl who's doing, again, working with touch counts, and she's 5 years old, experiencing it for the first time. And what I invite you to do, I can't see what you're doing, but you can watch what she's doing. But if you really want to experience what she's doing, is to simulate what she's doing with her fingers. So actually put your finger on a hard surface and repeatedly touch it in the way that she's going to be doing.
Okay, let's do just some numbers first, okay?
Numbers?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 4, 15.
How do you get
6,
this game?
17, 21, 22, 23, 24, 25, 26, 27, 28.
Okay, so I'm sure you could imagine what that would have looked like in a transcript and how much you would have missed. And when you see the video, there's lots of things that you can see. And what I'd like to propose is that by reenacting, there's still other things that we can experience that would
let's
not
do
have
just some numbers first.
possible.
Okay. Okay. Let's do just some numbers first, okay? Do just some numbers.
I'm not able to stop the video. Maybe if I go back. Okay, here. So in attending to what was actually done, we can feel things about the choices, about how the girl is tapping and how that matters to how she's understanding ordinality. So what not only what was done, but what could have been done differently, what was not done in that tapping. And we can develop a sense of sympathy for what it is she's doing, which I think can help us understand a lot about her mathematical thinking. So to close, just to provide some overview of how philosophically I'm thinking in terms of aesthetics, I've listed some of my key sort of influences here. And some questions that I have are there methods in the philosophy of mathematical practice that would be useful for us in math education, perhaps not reenactment, but other methods that allow us to talk about some of these aesthetic aspects of mathematical practice? And my second question is, how do the values, whether they be ethical or aesthetic, that are at play in mathematics shape the way mathematics education happens and mathematics education research? Thank you very much. I am going to stop sharing. I'm going to try to stop sharing.
Okay, thank you, Natalie. Thank you very much. Can you hear us?
Yes.
Natalie, can you hear us?
I can. I'm just sorry, trying to find. Okay, here we go. Okay, maybe I should stop sharing. Oh, you did it. Okay, good.
Okay, so so I think that the easiest is that if you want to see people, you can just come down and ask a question. There'll be a lot of moving around, but that's okay.
I can use the very light if we want to.
Yeah, but then at least you can see the people coming for a small walk. It's okay. So questions, comments? Would like to start? Yeah, go ahead.
Hi, sorry. Thank you so much for your talk. I'm just interested, like your definition of aesthetics. I understand you talk about is about sense making. Does that still relevant to beauty, or is completely different? Or is that? I feel like with beauties, you can still, you are sense feeling beauty. You are sense making like aesthetics values. So is that for you is like completely different things? Like aesthetic value is values, but sense making is something different. So value cannot be experienced in this kind of way. So is that clear?
Yeah, I think so. Thank you for your question. I do think that there's a strong connection between what we call feelings of beauty and sensing. I think you sense beauty the same way you sense ugliness. And I think in math education research, we focused much too much on beauty, also in mathematics, which is just one of the ways in which we can sense or judge mathematics. And in math education research, I think we should more on the ugly, since that is probably the most important experience that students have of mathematics. So what I'm trying to really get at is, how are the senses involved in those judgments of beauty? And that's where your philosophical positioning is really important. If you think that beauty is some kind of objective feature of mathematical proofs or theorems, then you have a hard time explaining how the subjective sensory experience functions there, and how, let's say, norms of what counts as beautiful in the community feed into those forms of sensing. So the reason why I find Rancière's work very interesting is because it puts the two things side by side and helps us look at how they interact and depend on each other.
Okay, great. Thank you so much.
Yeah. So hi, Natalie. Thanks for the talks. Really interesting and inspiring. I noticed that you don't mention any of the 4E stuff that's been consuming analytic philosophers. If it isn't useful to you, no reason why you should, but it's kind of interesting that you're doing this and they're doing that. But my question is,
4E, like the embodied cognition stuff, or?
Yeah, it was embodied, enactive.
Yeah.
And I can't remember the other two, but you know those people, right?
I do, yes.
Richard Manari and all that crew, yeah. My question is, you quoted Bill Barton, this rather optimistic thought that if we get, if we go at language the right way, then colonialism and every other kind of oppression will be finally vanquished, which would be nice if it was true. But the later part of your talk looks like a very direct challenge to that, because if the haptic and tactile and embodied aspects that we were learning about by watching the little girl with the iPad, and I'm convinced that is as important as you argued there, then Bill can't be right, can he? Because we could get the language right, miss the haptic stuff entirely, and all the evils of the world would still be kind of able to inhabit that area. Does that make sense?
Yeah, I appreciate that question a lot. And again, I think that depends on your philosophical position. And I think that one problem in math education research is that we've separated all of those theories of embodied cognition from all the sociopolitical theories that talk about language and politics. And actually, there's nothing more embodied than speaking and writing, right? Like I can't speak without my body. My throat is jiggering. I don't know how to say what my throat is doing, but it's involved. I'm spitting. It's a very embodied thing. So how I like to see it is, instead of splitting those two things and saying that they're somehow like ontologically different, is to see how they're actually related. And I think one thing that theories of embodied cognition give us is that when I say something like triangle, am I just saying the word, or am I also simulating an experience of having seen and perhaps moved a triangle, moved myself around a triangle? So the language and whatever the body is doing aren't separate, but feed off of each other. So I do think you're right in calling out maybe Bill Barton. I don't think that's how he thinks about language and mathematics, because I don't think he necessarily buys into theories of embodied cognition. But it's how I think about it.
Right. So to rescue him, he needs to start thinking like you. That works for me. Thank you.
Thank you, Natalie. I think that you answered to one of the questions in the chat, because someone was talking about simulating by way of imagining.
Oh, sorry, I don't even see the chat. I'm so
but
sorry.
I think you just answered to them to some extent. But I have another question. Thank you very much. It was great. No, it's terminological. So for you, your use of aesthetics is, completely is the same as your use of embodied. It's just kind of a follow-up, or is there something that is more in the embodied or in the aesthetic? Because it looks like you're using aesthetic in a etymological sense.
I think that I have in the past used aesthetic as being sort of more or less equivalent to knowing your senses, which isn't the same as embodiment, because there are many theories of embodied cognition that are actually quite dualistic, that see the body as like a helpful mechanism, but then it's ultimately the mind that does all of the actual mathematics by producing schemes and abstractions and so on. So I don't think about it that way, but how my thinking has changed through the work of Rancière is to identify how these waves of sensing are inevitably caught up with what we decide we're going to count as sensible. So with the Bourbaki, it is not sensible to look at diagrams. So you can't sense them. They're not available to the senses. 10 years ago, people would not have, if I had said, oh, let's use touch to do mathematics, people would have been like, what? They wouldn't have, that wouldn't have come across as sensible. So, and the reason this links, I think, to what the previous question said is that, mentioned is that because it's always a distribution of senses, there's always going to be some things that are considered sensible and some things that are not. There's no utopia in which we all think everything makes sense, right? That's not how disciplines work or how learning works. So what I'm interested in as a mathematics educator is how can we shift those distributions of the senses so that different people can actually be invited into doing mathematics than the ones who are typically invited into doing mathematics. So it's ultimately political, I think.
Yeah, it's a matter of choice to some extent. I mean,
yeah, absolutely.
Conditions by our senses and how they work, but it's a matter of choice.
Yeah.
Thank you very much.
Thanks for the question.
I'm going to ask a question myself. So I have a question about how the sensing of numbers relates to the research of the core knowledge of numbers and numerosity. So do you think that there's several ways of thinking about that? So do you think that these are just different way of accessing much more abstract representations by touching, by hearing, by seeing? Or do you think that there's something like more specific involved in the sensing and in the touchings that somehow is not just one way of getting at more abstract structure eventually? How do you think about this situation?
Yeah, so I really think I follow Davis in thinking about mathematics as being plural, by which I mean, I don't think that there are abstract mathematical concepts and we merely get to them in different ways, because that leaves the mathematical concept as some kind of Platonic transcendental thing that we could just, try to find different ways of getting at. And what I like about the people who are doing grounded cognition, especially people like Barcelou, is the way they speak about concepts as basically a capacity to generate infinitely many conceptualizations of a category. So why I think technology is interesting is because it gives us these different ways of generating those conceptualizations that don't just converge into the one concept of number. Because when we think, we don't actually think about the concept of number. We generate, we simulate experiences of number that we've had over time. Over time, there's quite a bit of overlap. And so we sort of get fixed on certain ways of thinking about number. I also think this aligns with the way Thurston talks about the derivative in his famous paper about mathematical proof. He talks about the 33 different ways of thinking about the derivative, less about there being one category of the derivative and 33 different ways of getting at it, but how each one of those ways is kind of a different layer that we maybe access through some kind of, quantum process or something like that. But I think I thank you for asking the question, because I think that is an important question in terms of thinking about what we think mathematical concepts are.
Right. Yeah, I wasn't so much thinking about the mathematical concept in themselves as in terms of just abstract presentational structure in the mind that could be called by different processes and then interacting with them, which I think is compatible also with what you're saying. Or am I wrong?
Yeah, no, I think so. I think as long as for me, it's really important that mathematical concepts are abstract and concrete. And that the reason that they're always going to be concrete as well is that they're always going to be accessing some layer of experience.
Right. Okay. Are there other questions? No. I have other questions, but I think that's the part, right? Okay, so thank you very much, Natalie. We're going to close the session now.
Okay. Thank you very much for having me, and I hope you have a good evening.
Thank you. You can stay around in case some people want to talk to you.
Okay.
So we're gonna, like yesterday, we have dinner around 7 at the hotel, and otherwise you're welcome to do whatever you want. Thank you very much. Bye bye. So
I'll be back in 30 seconds.
Yeah, sure, of course.
Yesterday we had a place for people who hadn't booked to come to dinner. Anyone wants to come who I hope I didn't before. So anyone didn't say they wanted to come.
Amazon delivery.
Is that you? So what time is it for you now? 8?
It's 9 o'clock.
9 o'clock. Okay, it's not too bad. Okay. I think everyone may be a bit tired as well. That's in there.
So are all the talks on the YouTube channel?
Oh yeah. So you can. So actually, the YouTube saves the talks once. So it's shown live. Then you can. I think you can see yesterday's talk recorded. I think the plan is that at some point we may change them properly and put them on the Borough Center channel. Okay. You want to say something?
Yeah.
Go ahead. Want to eat it from the camera?
No. Hi, Natalie. Thank you for the talk.
Hi.
I had a question about the last example that you gave. And in particular, I thought your comment about sympathy was really interesting. I was wondering if you could say a little bit more, and in particular, if you think that most of the time when we ask students to show their work or to show their process, if you think part of what we're doing is trying to sympathize with their reasoning.
That's an interesting question. I think it probably depends who's asking. I think some people are just trying to extract, the words that they want to hear, because that's part of what we've taken in our current distribution of the sensible, is that words are how you show that you know. So the way I was thinking about sympathy was a little bit more, what are ways of showing what you know that don't depend on words, but that I could experience myself if I was doing it, and a very different sort of sense of sympathy. But if you send me your email address, I can send you a paper that Liz and some of her colleagues wrote on sympathy, which you might find interesting. And it was kind of in that sense that I was using it.
That'd be great. Yeah, I'll send you an email. I also really liked your opening slide picture. Is it a painting of cobordism?
The one on the left?
The one, there's a painting on your first slide.
Yeah, that was a diagram that was made by Miriam, in her mathematical work.
Okay, yeah, I was gonna say it was very mathematical, but it also looked almost like an abstract art painting.
Yeah, I thought so too. Yeah.
Very nice. Well, thank you.
Nice talking with you.
Yeah, everyone can hear, because I don't know how to.
Okay.
So like the word, everyone can
We
hear.
are still on.
Yeah, but
I'm just telling you.
I don't know. Yasin is worried that I'm saying something that.
No. I just want to tell you that it's not.
But I'm
private.
just saying goodbye.
Okay.
Maybe I emailed you.
Yeah, that would be great.
And keep this connection. I'm sorry. I have the feeling that it break because of COVID. But,
Yes.
Broke. See you soon.
Okay.
Thank you very much. It was great.
Bye.
Are you good? Yeah, I think everyone said what they. Yeah, thanks for coming. It's too bad that the other talks would be too early for you to.
Yeah, I'm really sorry, but I will watch them.
Oh, cool. Thanks. How is your work going?
Oh, it's okay. It's okay. I have now I have to run to the university and do meetings all day. So this was actually the fun part of my day.
Okay. Then we'll leave you to it, and then we can always talk. I hope you have an okay to see you in Europe.
Thank you. Okay. Bye.
Bye bye.